Westervelt will join. He will also join online for his session on data correction and calibration. For his session, James and then Cosmos would assist Dan because it's mostly hands-on or practicals, and because he will be online, they will be assisting him here physically. In the afternoon, after lunch, so we might have just about 40 minutes lunch break. Please bear in mind, we are trying to make sure you get the best out of this workshop. I hope we are all clear on that. So we can proceed now. Welcome, James.
So I think today we will try and then finish up what we couldn't finish the last time. So I'll just do a bit, I'll do a recap. So I've tried to put everything in the Jupyter notebook. So when we met on Monday, I think we were able to, the first bullet, we were able to kind of import data using the pandas, the read Excel function into our Jupyter environment. We were also able to assess the types of data, whether symbol, datetime, font, everything, using the .info function. And then the third bullet, we were able to use dot to datetime to change the date format of our data set. And then the fourth bullet, we were able to transform or rename our column headings using the .rename function. So today's session, we will try to filter our date using the .isIn function and then some Boolean marks kind of operations, and maybe some logical operations to subset our data set. And then finally, we will try to plot some hourly, weekly, season, plots using our some kind of box plot line and some few if you have the time. So if you can open up your notebook, and then we will just try and work from where we ended. Okay. So I'll try to kind of copy each bullet to where we will kind of so that at least it will guide everyone in case you want to pick up this notebook for your work. So I'll copy from here. I think we are done with the first, second, and third. So the fourth is to filter our data using some functions. So when you check what I sent earlier, I tried to put some few information with as to how to use the .isIn function. So like I gave an example that if you want to kind of filter your data, whether maybe April, May, June, or December, January, February, like that's the Harmattan season, you can use the .isIn function. So I'll just kind of apply this function to our previous data that we are using, and then you see how it works. So let me just copy this one and then put it at one cell. Let me just copy it. So we have done all of these .info, set index, and all of that. Okay. And then I think we couldn't even finish this one. How to even collapse these columns as row we can be able to collapse these column headings, and then make them as row, and then set the value as a column heading. So this function is able to do that, to collapse our data from column to row, sorry. Let me just put a line here. So we use the pandas.met function. So this is our name of our data, that's Afri-SET _new. It's here. The ID variables that we don't want to collapse, we need to also state that. So we have put it here. That's the datetime. We have the datetime column intact. And then the variables that we need to collapse into rows. We have the sensor A, sensor B, and sensor C. That's the PM2.5. So these are the variables that we need to collapse. And then the name of the heading for that column should be, let's say, let me just name it as maybe sensor type. Let me say sensor type. And then the value of this column we should give it a name. So dot name equal to, let's say, value. Okay. So that one is done. We can run our cell. Yeah, so that's it. I think it's run. Let me see what we have. I think we have. Oh. Okay. So I'm taking my time to run this. I think we have the pd.melt is able to collapse our columns. That's sensor A, sensor B, sensor C columns, and put them as rows. So if you can see on my screen, I have done that using the .melt function. That's what's its job. Try to merge all the columns together as one, and then assign each value per row of each column, and assign each value to that sensor. So that's what we are seeing here. From here, we have each column per each sensor. That's sensor A, sensor B, and sensor C. But I didn't want to collapse the date because the date is serving as a reference. So this is what I have to set it here. That's ID variables, that's datetime, should remain intact. But the ones that I need to collapse are the sensor A, sensor B, and sensor C. And the name that I will give to the heading of this row should be sensor type. And then the variable name should be value. So this sensor C values are the ones that are appearing here. These guys. Okay. So if you can run this, but if you can't, don't worry. I'll I'll send this code to you so that you can just do it by yourself. So this one is done. The next task is to at least rename this value. I mean, I think we know how to do that. So we can use this function, that's .rename, to rename the name of this, maybe 2 p.m. to 45, okay? And then this function tries to take only the hour portion of the date. So we have hour, minute, and then seconds. So that the t dot strip time will try to take out the hour portion of our date. So let me just copy this function and then maybe put it here so that you see what it will do to our daytime column. Let me put it below it. So I am trying to give a new column name for our new extraction. So that's hour. And then this is actually mine. So let me just rename this. Okay, I've assigned this one to it, so that's fine. So that's my variable name for the data that I've retrieved. So that's the name here. And then we want to extract only the hour from our daytime. So once you run this, you have the hour portion of our. So it's being run at the moment. So now I've been able to extract only the hour portion of my daytime. That is this guy only from the entire daytime. So now we have this. And with this, we can be able to group our data per the hour. With this guy here, we can be able to group it per this column. Okay, so we have from 0, that's 0 is actually 12 a.m. Then we have 6:18, that's 6 p.m. And then 16 is 4 p.m. That's the UTC time, okay? And then we can go ahead and then also do same for the week, that's the day, the same way as we did for the hour. We can do same. Let me just put a column below it. Okay. Let me add one more. The same way that we did, we can just extract only the day. That's 19th from the month. Afri-SET underscore data. When we run this code, you see, it will just extract the day from our daytime, okay? Whether it was Monday, it was Tuesday, it was maybe Tuesday and all of that. And this will help us to actually kind of group it the way we want it to be. So with these functions, you can be able to kind of tweak your data the way you want to see the changes of your PM data, okay? Let me just go to the next one. And then, so I think I've already done this. I will not use this. Let me just go to the month. Okay. What's happening? So this function here will set whether it is a weekend or is actually so whether weekend or weekday. Okay, so the same way as we did for the hour. So it goes on and on. I try to put much information so that at least in case you get this code, you can use that to for your work. I mean, So now we have whether it was weekday. So Monday was actually a weekday. I mean, so Monday up to Friday is weekday. And then Saturday will be a weekend. So with this kind of information, I think I'll just do one grouping that you will see how we can kind of be able to visualize our plot. And the month, let me do the last one, the month thing. So now we have the month here. And then if you want the seasons, whether wet season, dry season, harmattan, we are going to use this code. So as I said earlier, the Boolean, I think our fourth aim is to try to filter our data using the is in the Boolean max. These guys, the is in function, the Boolean max, or the logic operations, just to get more information. So whether we want the data to be in seasonal format or like kind of see if this month is actually wet season or dry season, you can use the logical operations to set it to our liking. So let me just go and copy that code, and then so here for this workshop, I assume that April, that's the form, is for wet season, and then I think April, May. So this is April. April is for our wet season, and then May is our dry. But in case you get your rare data, where you have all the seasons intact, you can set all the month that you want, whether you want in Europe and North America, they have spring, fall, summer, and the cool. But here we have two seasons. We have the wet and the dry period, where the wet starts from, I think from March to, I think October or so. And then we have the dry season from November to March. So we can just set whether you want it to be, let's say if you have fall, let's say from May, June, let me say 5, 6, June, July, August. Let's say this is your wet season. And maybe for your dry, we have November is 11, we have 12, we have 1, that should be in January. We have 2, that would be for your February. And then let's say March for your the 3rd. So we can have this to actually set up your wet and then dry period. Okay, but for this training, let me just remove all these months from, and then let me just maintain what I have done already. So when this code is run, you will have all the months you want to set as your wet and dry. The comma. Okay. All right, thank you. So this function will just try to get all the wet. Let me just run that. It's run. So let me just kind of visualize so that you will see what it has done to our data set. So let me just go down and put it here. So we have the season there. So that's the last column. We have the 4th month to be wet. And then we have the 5th month to be our dry. I think, let me go back. The dry, let me just remove because we don't have any other. Let me just remove this. Yeah, should be dry. It should be dry. Yeah, S. So let me just say S. Oh, I think lady should be 5. Lady should be the else, yeah, they should. Hold on, right? The month. That is all right. Okay. Okay. Let me just go back. Let me just go back. Okay, so I think that is done. So in case we have any, I can remove this from it so that we will have. So now we have our feed, that's our May to be our dry, and then April to be our wet, okay? And then once this one is done, we can go ahead and then maybe remove, if you want to remove any negative values, or let's say you want to kind of set your data to be from 0 to upwards, we can use this script to do that. Let me just quickly run this code, and so that at least we can remove any zeros or untoward data points from our. Okay, so that one is done. So now we have a clean data set from our analysis. So we can go ahead and at least try to plot or group it. So here, I try to kind of take some of the data points to be able to group it, okay? So I was grouping it by hour, and then finding the mean after the grouping. So I chose the date, the daytime, the hour, the sensor type, and then I renamed the value. That's what I've renamed the value as PM 2.5. Okay. And then let me just do it. Okay. And then I group it by the hour. So once you run this script, I've done that just to see only the hourly pattern, whether we have either morning peaks, afternoon peaks, or evening peaks. And here I'll try to reset our index to be kind of default. And then here is where I use Seaborn, okay? You have this code, so I mean, just watch as I run this. So once you have this data point, it's easy to actually see more. If you want to do more, you have the luxury to plot as many graph that you want, just to see what is happening in your area when it comes to PM 2.5 levels, okay? So from running this script, I'm seeing that in the morning from 12 a.m. to, let's say, 8 a.m., that's 8 a.m., we have a morning rush peaks, okay? From all the sensors, that's sensor A, sensor B, and sensor C. We have a morning peaks, but in the afternoon, we don't have peaks. That means we don't have people going to the market, or there's no vehicles going to work. At least the people going out has been minimized. There's less activity in the afternoon time. But in the evening, because here, the way here Accra works, every morning we go to work, we get our trotro, and then we go to work. We have so many people also burn their trash in their homes. And also, car fumes from trotros try to kind of elevate PM levels. But in the afternoon, and even traffic, as someone is saying, traffic, it's true. So there's traffic in Accra. But in the afternoon, there's less activity. You have less level of pollution. But in the evening time, people want to come back to their home. There's huge traffic. You will see many people trying to board cars to their homes. You know, I did same work in the US. In the US, you have afternoon peaks because in the US, people want to go and have fun. So you see that in the afternoon there are peaks here, but in the morning there's less because they have good bus system. So and they all use gas for their fuel, so you have less peaks in the morning. But here it's different, you know. And then if you try to have a bar plot of all of that, and I will say one more thing here. So at Afri-SET, we try to group these sensors. So from this graph, sensor A is overestimating PM than sensor B and sensor C, right? But they all have the similar, the same pattern. But for sensor A, we have higher values of PM 2.5 than the rest. Then it's followed by B and then C. So this is how, at Afri-SET, that's how we try to kind of see if what we have at our center, they all agree, okay? And if we see this kind of pattern, that's where we apply our calibration models to make them come in line, that all of these guys should fall because they are found in the same place. And so they should have the same values for PM 2.5. Okay, so this is how at least we try to know what is happening for PM 2.5 using these sensors. And then we use bar plot. So here I try to group it. Let me just remove the hue from here so that it can be more visible for us to see. So here we have the bar plot for the hourly, and we can actually see the peaks falling below in the afternoon, and then we have peaks in the in the evening time and in the morning times. Okay, for the bar plot, for the box plot rather, let me just try to remove the hue so that at least it will be more visible for us to see. Yeah. So I can just remove the outliers. So now you could see that from 12 a.m. to 11:59 p.m., you could see the PM 2 and 5 patterns of this census. Okay, we have more peaks. So let me just try to bring the hue so that at least we can see which one have more outliers than the other. So hue, we go to sensor type. So I think sensor A has more outliers than the B and the, which is obvious as we saw from the diagonal plot. So we can remove the outliers if you want. So that show lies. You go to false. I think it's flies. Okay. Dodge line width. Bar plot. Okay. Let me see. Okay. This will come from this. I think it should be outlier. Yeah. I think that should be the flyer. I think flyers. So basically, that's how we can be able to kind of visualize. We can do more. Let me just try to figure out. I think here will be. I think out. Out. The F, right? No, I think the F should be there. I'm trying to figure out how. Okay, let me see. Oh. So those who have used Seaborn before, normally I use plot, that's matplots to do that. I think it should be maybe let me try to put S here. Let me see. Okay. So here, that's the S. Okay. So you can just either remove this guy to show all the outliers. Or you can just add it to just to make your plot nice. Okay. And then if you want to kind of put, so here, let me just add some few things here. Plot.figure, figure size. Okay. So let me just put one here. Okay, so that they will have the two. Okay. So I've okay, so that's fine. Okay. Then let me do the same thing for this one, so that at least they will all know how, in case we don't want this one, you can find the other from that one. Okay. So here, let me add the hue for the sensor type. Um, Let me add some comments here so that at least you guys can have it. Okay. So here, displaying all the sensor types. And then here, showing only PM bar plots, PM 2.5 bar plot here, or PM values. Okay, so this is just one way of trying to at least visualize your data. We can go ahead and group it by season, or we can go ahead and, because we have seasons, right? We have monthly. Let me just display our data set here. Because we have seasons, we have month, we have day category. We can have a box plot that will display what we want to see. Let's say, let me just copy this script and then put below this cell to display only the seasons, okay? So here should be season, not sensor type. So season, we will have, okay, this should be data. Afri-SET data. So here we have season, not sensor type, to see if we have PM 2.5 values to be higher, whether in the wet or the dry season, okay? We can go ahead and do for the weekday. Let me just copy the same script and then show for only the day category. That's day category. Let me just copy this. Yeah, we will have the day showing whether it's weekend or weekday. Yeah. Okay. So you could have so many plots as you want. You can even use the bar or the line graph to just display all of this. So here I just use the hue that's sensor type. Here you can use either, I think I just copied, only I can just group it using the weekday or weekend. Let me just do that so that at least we can have some kind of variation in here. Let me just group it by the either season or weekday. Let me just do it for here so that we can see. We have our, instead of our, let me use month. We have month here. We have day. Then we have, let me just use the weekend and let's see if it will work out. We have day category. Let me just group it by day. Day. We have day category here. Then let me say season. So we have day, daytime. Let me say month. Okay, so we have this. Let me just reset the index again. We have this one. So after having this, we can go ahead and plot whether we want it to be weekday or day or whatsoever that you want it to be. So let me just put it here, day category. Category. Let me say here to be day. Let me say this year will be daytime. I'll say daytime here. Yeah, daytime. So you could have so many stuff. We have here to be weekday, and then we have the other one to be kind of weekend. Weekday has higher values than the weekend. And let me just put Y to be PM 2.5, but at least it will be quite visible for us. Yeah. So so once we do have this to be set, you can have as many as you want, plot that you want to have for your report or your work. Before you watch your article, you can explore all of these. Okay, we have weekday to be higher than the weekend, as you can see from this graph, going up to 80 milligram per meter cube than the weekday around 60. Okay, we can add more things here. I mean, put some few kind of decorate our plot as I was doing plot dot figure and figure size equal to, let me just add some few, maybe 15, 8. So from Victoria, we have more time. So if you can just try your hands on any of these before you get the code, so that you can ask questions so that we can all try to solve it together. Okay. So if you have your Jupyter notebook open, try to let's say from here, from this side, yes, from this side, try to decouple only the hours from the daytime using this script. Afri-SET data hour, that's for the column, and then you use the T dot strip time to decouple the hour. Okay. And then you can also try the dot day to do that, just to get the days from the daytime. And then if you have any other questions, please, you can ask before we end the session. But I can go ahead and do more, plot more graphs. Okay. So let's try and do some kind of coding by just trying your hands on and then ask questions in case you have questions. If there are no more questions, maybe I will just do the is in function. The is in function. Let's say from June to July. Okay, you can use the is in function to take out some period from your frame, your data frame. Okay, so let me just go ahead and do that as you try your hands on the other ones. Okay, so here I just gave an example that the is in function try to take out some months from your. So let me just do this, copy this code and put it here. Only this function can help you get. So let me just say that we have our April to be our wet season. Put here 4, and then let's say our dry for our that will be our dry season. So let me say dry season. Dry season, let's say 5. Okay. This function will just take out only what you have given. So we are saying that the 4 is our wet season. Okay. The April, that's the 5 is our dry season. So dot is in function will just take out or filter only the April month from our data frame. Okay. So running this code, we have our month set already. Let me just go ahead and run this. So let me just see what we have in our. I think I use Afri-SET rather, not data. So Afri-SET data here. And then I have Afri-SET data should be here too. And here I'm using 2 list functions, list of lists. I have 2 list functions. To be able to do this, you have to have 2 lists of functions, okay? Let me just put that I can explain better. So in order to use the dot is in function, our first is to have one list function or the one list box. So if we have Afri-SET data, one list, so the square box is our list, okay? This is our list, and then we will put another list inside our first list. So we have Afri-SET data inside of our list, and then we will specify the column that we want to select our month from. We put another list inside and put our column name inside our list, that let's say month. And then we will bring dot is in function. Then we are done. Then here we can put our month in, whether for that should be our wet season inside. Then run the code, you have your data, taken out from the other month, okay? So let me just go ahead and run this. First, you should be able to know how you have named your columns, okay? So here is month, but let's check what we have given it to our frame. So Afri-SET data. We have months here. We have months as our column name. So we are good to go. Okay. So once we run this code, we will have only the months that we want to specify kind of taken out. Said we want only int values. So that means that we are not giving the month as, so let me just see our our values types in our data set, okay? Let me just put one here and then just see what we have there. We have here Afri-SET .data .info. Okay, so we have our season to be object. We have our amount to be in int, which is okay. But our 20.5 also in float, which is fine. Daytime is also fine. Month is also fine. So what is the issue here? Okay, object like values should be passed. Okay, it want only object. Okay. So let me just, so here you can just change so let me just use season as an example so that I won't waste time here. It wants, so let me just use, let's say, wet. The spring, it wants an object. Let me specify the thing here. Let me say, this is a month. Equal to, let's say 4. And put the month here. So it's trying to tell me that it doesn't want to have any int in here. Okay. So what I've done here is just assign what I want to take out. Okay. So I want to just take out the fourth, the number 4. That is our April month. So month it should be 4. That's my assignment. I mean variable here. Once I put the month inside my is_in function, it's going to retrieve that thing from our data frame. You can go ahead and do for the dry season as well. Let me say this is my wet season. My wet season. Let me put it here as my wet. And then run it. It's giving me only the wet season. I'm seeing wet. Data form. Oh, okay. Because I haven't assigned. Let me say wet equal to wet season. Okay. Months. It's saying it is not seeing anything, but it should be. Okay. So data month. Okay. Okay. Then let me go ahead and do for the dry as well. So let me say dry. You put that in, you can just say, 4 or let's say 5. And then just copy the code and put it inside. dry season. You put your dry here. Retrieve only the dry period for you. Pass into okay. List. That too is run. So, and then the other one too is using the bitwise to do that. So this code is another way to use a bitwise. That's the OR function. The OR operator to select your period, okay? So here we have our Afri-SET, data here. Afri-SET is here. Afri-SET data should be here. Afri-SET. Okay, let me just do for only one. Wet season should be equal to 4. And then we don't have enough month, but let me just do for only one. So this will just pick out only our month for us. You want me to add more? Okay. That is the issue. Yeah, this one. Oh, Lord, please. Oh, thank you. So, so one that is run, because we will have it. You have our month being taken from our data points. So that's how coding is. So once you forget one, you mess up. Showing there. I didn't even say that. I didn't even bring the square bracket here. I didn't see it. Thank you, Doc. So the other point is to add the logic function. Okay. So this one will just use what we have done so far. That's the last one that we have done. So we have this, as I have explained earlier, the wet, the dry, and everything. So in case we have, let's say 4, we have 5, we have 6, we have here to be, let's say 12, 1, that's February, and the other is, and then, so that would be it. So once we have this, our data assigned to it, to run it, Afri-SET, reset data set, Afri-SET. Okay. So this will just give you what you want, okay? And then this apply sign here will just assign what you have given here to our data frame to give you what you have assigned to, and then that will be it. So guys, this is how you can be able to at least tweak your data to see what you want to get. I try to put in so much like information just to give you a brief, to have the luxury to at least take command of your data from scratch from here. If you don't want to, read by the Excel, you can save your data using CSV. So CSV, you don't need to use Excel. You have to use .csv to read it, okay? So let me just add it beneath that line cell. You have to use CSV to read your CSV file in case you have a CSV file, okay? The second one is, the first one is to read Excel. Read Excel, okay? And then in case you want to change any other data from here, you can be able to do that. These guys will help you in I think actually the afternoon session. If you are doing the calibration, if we are able to do this, our session for the calibration exercise will be easier because then we use Python to do that, okay? So how you will read your data into your Jupyter environment, how to set the time, how to change some variable names, how to filter out some data points. You have it all, okay? So it will be easier for our afternoon session. So please, if you don't have any, if you have not tried it for yourself, please do it now so that it will be easier for you when we are doing the calibration. Because I think Dan is online, it will be online, okay? He will try to code it online. And so if you are able to do it by yourself using this kind of coding, at least some basis from your end, it becomes very easy for every one of us, okay? So I have put the code here to read the CSV file. Let me change this to CSV. And then what else? To check for the types of data that we have. We have float, we have objects. In case you have to change that, you have to change it from here by seeing this. We have to change it to datetime. We have it. And then in case you want to set the index to datetime, to date, we have it here too. In case you want to also rename your data to, you can do that from here. And here, in case you want to take out some pure from your data types, you can do it from here also. So I think you have almost everything. Yes. Yeah. Maybe I'll just put a cell here. At least it will guide. So for me, you have so many information that will guide you. Let me just put here. Let me just put it from here. That will guide you in case you want to apply this same use pattern to filter your data point. Filter data frame. So I'll try to share this script before the day will end. And if you run the script and there's issue, please let me know, okay? So that at least I can try to kind of try to solve it together. So I'm marking the script with markdown so that at least it will guide you as you apply the codes, okay? Let me just go to the plotting and add some comment from here so that at least it will guide you to Let me put one cell here, and then section for plotting. For plotting. Okay. Yeah. Okay. So I think someone is asking a question online that how can he get the data point? I would upload the data plus this script to the Google link, all these data points that we have used. And I think I didn't even add one more thing, how to save it in case you don't know how to save this bar plot. Just use, let me just add it from here. Let me say, this is my bar plot, save as plot.save as. Let me see, let me just add some few things so that at least I can maybe plot the X label. Please, do you have any questions so that I can add up? Maybe let's say S label should be hourly. Hourly, and maybe Y should be Y label should be maybe 20.5 values. And let me just expand the figure a little bit. Figure, let me see, fig x equal to plot subplot. On fig size. So we have, let's say, 15.5 x equal to x. So that at least to be, let me see how this plot will be. Is any question? I'm trying to figure out, add some more information to the figure size, okay? Let me just put some things in. I think we didn't also treat how to set maximum, minimum, duplicate, and all of that. We didn't do that. So if you want, I think Matthias did that in his session. But if you want me to add all of that in the this script, you can let me know so that I can just add all that information inside this script. Please, do you want me to add it or? Okay. Yeah. Okay. So then maybe I'll add everything, and maybe anything that you want me to also add, you can let me know. Okay. At least the basics. Okay. So I'll just add the duplicate session, maybe add the maximum, minimum, but you can just use summary to get what you want. Maybe you can just, it's very simple. Maybe, let me say, if I have one here, if I want to maybe Afri-SET data, Afri-SET maximum, PN2.5 dot max. It will give you the it will give you the maximum value. If you want to get the minimum to the same thing, minimum, to give you the minimum value, okay? And then if you want to check the duplicate, the same thing, the same approach that you will use. So I'll just try to add some session that can check duplicates for you. Duplicate, okay? That you will see all of that. Okay, so we have 10 more minutes to go for our breakfast. I think Dan will use. So please, Dan have shared the data that you'll be using for the calibration in the Excel, the Google link. If you don't have it, please use this time to download the data. And the way we have done for this, copy the data and the script inside the folder, and then try to upload the folder and the data using the same approach. Okay, how we are able to assign the .os function to import our data set, right? Set this thing to your path. Okay. So then I've put the data and the script, the link in the WhatsApp group. Okay, so just go there right now, copy the script and the data inside a folder on your laptop. Use this function os.hchddir to set the path of your folder. That's the path here, okay? That's the path. Right? And then if the data set is actually in .csv or Excel file, use this approach, whether read Excel or read CSV. Then you'll be good to go before we start the afternoon session. Because I'm not sure that maybe he will delay like the way we delayed the last time. Okay. Yeah. Okay, just use the same approach here to just go to Dan's data file. So first you check the information like the summary, whether the date is actually in daytime. You check the numbers, whether they are all in float. If you find that the date time is actually in object, you use this script dot to datetime to change it to date, okay? Okay.
Shall we give it up for James? I think he's done well with us. For the next session, we have Professor Gift Dumedah online. So Prof will be taking us through ethics in air quality. A brief introduction about Prof. Hello, Prof. Can you hear me?
Yes, I can hear you, Victoria. Thank you.
All right. Sure. So Professor Gift Dumedah is an associate professor of geography and a senior fellow of the Transport Research and Education Center, Kumasi, at the Kwame Nkrumah University of Science and Technology here in Ghana. His interests include transport and mobility research, transport relations with health and the environment, urban dynamics, and geospatial information science and technology. Prof, please, we are happy to have you and welcome. Over to you, sir.
All right, thank you very much. So first of all, just 1 minute to just share my screen and then I'll take it from there. Okay. All right, good morning to everyone. I hope you can see my share screen. Victoria, can you confirm?
Yes, please, we can see it.
Okay, all right. And it's the audio coming clear at your end, please.
Yes.
Okay. All right. Good morning to everyone. It is an honor to be invited to be part of this program. And I first of all want to thank the organizers of the data quality, the air quality data analysis workshop. And also want to thank Victoria and Dr. Felix for the invites. And I am also privileged to provide this talk on ethics in air quality. I will have wished to be in there in person, but because of other engagements, I'm unable to be there this morning. However, I would like our deliberations on ethics in air quality to be a little bit more interactive and hopefully engaging with this session. So my task this morning is to be able to take you through some significance of air quality, which I believe in previous talks you have had some background information already, and also been part of the previous session where we are analyzing some air quality variables. That means that you have some background information there already. And then also talk specifically about ethics and some dimensions and considerations of ethics in general. And then we'll also be looking at human capability approach in terms of ethical consideration and some specific examples relating to data in Ghana. So just to provide a background, we really know that air quality is an important part of environmental health. There are several dimensions of environmental health, but air quality is one of those critical aspects. And it has quite a number of risks. One of them is health risks to human health. Specific diseases that relate to air quality can be, for instance, respiratory diseases, vascular problems, premature death are some cases of health risk. And then also air quality also, in many cases, disproportionately affects vulnerable populations. And by vulnerable populations here, we are referring to, for instance, children, the elderly, persons with disability, or communities who are living in informal urban areas. Air quality also have healthcare costs as well. For people who are affected by air quality related diseases, have to be able to seek health care to be able to address those illnesses. And in cases those capital costs or economic affordability is unavailable, that can become a health burden for a lot of populations. And air quality also has an ecosystem damage, not only for human health, but also environmental damage to soils, to air quality in terms of biodiversity as well. And of course, to climate change as well, where we have some air quality variables that can affect heating of the atmosphere or cooling of the atmosphere in this case, which can lead to climate change interactions. So as we've seen, there are quite a number of dimensions to air quality impacts, both human health, environmental, as well as climate change interactions. A key part of air quality is monitoring, and as has been indicated in our previous, we're shown some monitoring data from sensors that you have explored in your Python environments. So monitoring and regulation are a key part of air quality management. And once some of these monitoring data are available, then they form the basis for public awareness in terms of where are the risks to be avoided so that populations can take adequate measures to avoid those risks. Also, very importantly, local authorities can use that monitoring data to be able to implement some local action in terms of zoning laws, education to promote public health and things like that as well. Now, I will want to just provide some statistics or some information in terms of the severity of air quality. This graph chart we are seeing here is from the World Health Organization plot of, on the horizontal axis, we have the years from 1950 to 2021, and then the percentage share of deaths relating to various causes. And on the right here, what we see are some illnesses, and the ones that relate to air quality, for instance, cardiovascular diseases and respiratory diseases, and some of the what's the name? Some of the infectious, health-related respiratory diseases as indicated here. The key thing I want to point out here is the significance of air quality related deaths. For instance, for 2021, cardiovascular diseases, it's close to about 21 or 24%, while respiratory diseases, it's almost about 6 to 7%. So that is a global information on this, and it's quite a significance. All right. And also, another way of looking at the air quality related deaths is also to look at the various publications that relate to air quality deaths. And what we are showing in the first one is the World Health Organization mortality for the global average. So here we're showing the deaths of all sources in relation to air quality, and the total is about 70 million from the WHO. And in terms, if you break it down to indoor and outdoor air pollution, it's almost evens out. But this is the annual at a global level for each year, 7 million, which is quite significant, and it's compares to the entire population of Paraguay in terms of the 7 million. That is for each year. That is the number of people losing their lives to air quality related diseases. So the message here is the impact of air quality related deaths in this case globally. But we can also look more locally. For instance, these some information relating to only chronic respiratory deaths in selected countries globally, shown at the top there. And then we also have selected countries around Ghana. So we shown here Ghana, Burkina Faso, Cote d'Ivoire, at the African region, and Togo indicated there as well. So for instance, in Ghana, there are about, the average is about 24 out of every 100,000 persons who result in a death relating to a chronic respiratory death. Now, we turn our attention to ethics, having provided the background of the significance and the importance of air quality relating to fatalities or to mortalities. I'd like us to look at ethics in general. So when we talk about ethics, what exactly are we referring to? We're referring to questions that relates to human conduct or societal norms or morality in general. And in relation to air quality, we are talking about questions about how could air quality professionals conduct themselves in their professional matters. And why this air quality, ethics in air quality is important is that it provides a framework for decision-making processes relating to air quality, so that when decisions are made, there is an established standard to which we can gauge them. So, for instance, there will be basis in terms of what is fair air quality, or what are the rights expected in air quality, and what are the societal benefits and norms expected from air quality professionals. So when we talk about ethics in air quality, that is exactly what we are referring to. And Victoria, I don't know, I cannot see all the audience, but I'm just wondering if I could engage your audience in terms of what they might think are some of the behaviors or human conducts that might relate into air quality. Are they open to provide responses as I go ahead?
Yes, please, Prof. Please go ahead.
Okay, all right. So I really want to also emphasize that, please, if you do have a questions, feel free to prompt me as we go through this as well. Okay, so in terms of air quality, we also have standards, air quality standard, and we'll be talking about some of the air quality considerations or ethical considerations in relation to air quality. So as we have indicated, that air quality has a number of dimensions: human health dimension, environmental dimension, and biodiversity as well. So in terms of ethical consideration, these are some of the keystones to be used in terms of its consideration. So the first one is environmental stewardship. So with environmental stewardship, it's a principle that underlines that the current generation should be managing resources in a way that can sustain future generations. So when it comes to air quality management, some of the practices that are undertaken today can affect future generations, and that is the principle that underline environmental stewardship. And then we have also climate change. It's an ethical consideration to address climate change for today, so that future generations will not be disproportionately affected by climate impacts as well. Another key ethical consideration is environmental justice, which is the principle that analyzes that air quality benefits and burdens should be fairly and equitably shared among all population. It should not be disproportionately shared to only a segment of the population, but fairly distributed entirely as well. Now, and this is the aspect I will be delving into a little bit to unpack environmental justice in terms of ethics. Now, a key other aspect that we have to look at in terms of ethical consideration is there are several interests in terms of air quality, and some of these interests relate to economic interests, environmental interests, individual versus collective, and then in terms of short term and then long term. So for instance, when we talk about economic and environmental, is that there are certain practices, for instance, excessive use of certain vehicles that pollute the environment will have environmental impacts. And there are economic reasons, there are or capital that are needed to be able to clean up those pollutant, for instance. So it brings out the question of how do we balance the economic aspect or capital aspect with environmental damage that is being caused. And of course, also, there are also individual aspects compared to the collective, that certain individuals might be enjoying using certain equipment that pollutes, or certain machinery that pollutes the environment, to the detriment of the collective society as well. And then, of course, short-term and long-term, it's also another dimension or interest to be able to balance. And a key other consideration is scientific integrity and transparency. And With the previous session, I was very glad that data is being shared for people to explore. And this is very important in terms of air quality management, that data that underpin decisions and that underpin regulations or interventions should be made available to everyone so that they can understand how those regulations or those interventions have been arrived at. So scientific integrity is very important, and transparency is also very, very keen as well. And protecting vulnerable populations. Here, in terms of some populations are severely impacted by air quality, for instance, children, the elderly, low-income populations, persons living close to heavy road corridors as well. I'm sure you can think about other vulnerable populations, perhaps in your community as well. Now, when it comes to ethical consideration, there are also dilemmas. In other words, there are also cases where there are competing interests that we, as a air quality professional, you have to look into. And some of these broadly will have to relate to some of the interests I mentioned earlier in terms of balancing scientific integrity, public health, environmental protection, and economic interests. As indicated earlier, it takes a lot of capital to provide interventions for air quality cleanup exercises. So there are economic interests in that regard as well. And scientific integrity, that interventions should be based on evidence and good science. So this workshop is actually also laying the foundation for good science, that we are taking lessons to understand how we can analyze our air quality data, and that is part of scientific integrity. There is, in terms of dilemma, there also could be pressures to skew data. You could have analyzed the data, but you might be pressured to skew some of that data, and that pressure can come from diverse areas. It can come from employers, it can come from clients, it can come from public, or in different directions as well. And as indicated, balancing the interest from economic, environmental, and public health. And we know that air quality has public health impacts, but how can we make sure that economic development still goes on in parallel with public health as well? And a key aspect of which I've also underlined earlier was the aspect of environmental justice, which also relates to equal distribution or equitable distribution of benefits and burdens. Now, there are several air quality benefits. At the same time, there are also burdens. So some benefits of air quality is, for instance, where we might have parks, for instance, or where we might have clean energy, where we might have public transport that is clean. Those are some examples of benefits of air quality. There can also be burdens. For instance, if you are located close to a heavy a road corridor that has either high distribution of particulate matter or CO2 or carbon monoxide and all of that. And also being exposed to using low quality fuel for energy. So those can also be burdens as well. So we are talking about how do we balance, how do we equally share those benefits as well as the burdens. There can also be dilemmas about communicating uncertain risk. We know that air quality is underpinned by data, monitoring data or data from various sources and models. In some cases, the data can be maybe insufficient to make a conclusive decision. And that will mean that you might not have a full understanding or full comprehension of the risks that you want to communicate to the public. And that in some cases can also lead to a dilemma where as an air quality professional, you do not have a conclusive data to be able to communicate risks or exposure levels to society. And of course, long-term sustainability, there could be competing interests in terms of quality versus efficiency. So for instance, you could have energy efficiency cases or efficiency cases, and then also trying to have air quality. Sometimes there's a conflict in there, or there's a competing interest in that regard as well. And of course, holistic effects. We know that there are also impacts or implications that may be beyond air quality. There could be economic impacts, or there could be societal health issues that maybe be way beyond air quality, that it's part of the consideration for a particular project. And of course, hidden pressures from clients or employees, or from public as well. And then professional development, very important. This workshop is part of the professional development for us to know some of the cutting edge data analysis tools for air quality. And that's part of equity, building our equity as well. So in other words, you are already committing to equity standards by being part of this workshop. Now, a key dimension of equities, of ethics, is equity. And by equity, we are talking about social justice or distributive justice, which I referred to earlier in terms of environmental justice, which relate to fair distribution of burdens and risk. Now, sometimes this classification of burdens and risk can be construed, because for certain populations, that burden could be magnified. But a certain population, they might have the capacity to withstand certain levels of burden. And I would like to use this concept to unpack the equity dimension of ethics. So in terms of equity, it's a concept that we cannot actually measure in terms of operationalize, but we can operationalize it through what we call disparity. In this case, we're referring to as air quality disparity. So by air quality disparity, we are saying that we know that air quality is very changes in terms of space, in terms of time. And that it's part of the characteristics of air quality in terms of where the source is, where the circulation and all of that goes on. But when it comes to human welfare, we're saying that there is a type of air quality difference that can be tightly linked to economic, social, or environmental disadvantage. And what we mean by these disadvantages is that economic disadvantage could be a low-income individual. Social could be, for instance, like we are saying, children or elderly. Those are all social dimensions. We have social dimension, and then environmental in terms of, for instance, living close to a heavy industrial park, or living close to a waste dump. Okay, so these are various kinds of economic, social, and environmental disadvantage. We are saying that whenever there is air quality difference that is systematically linked to any of these disadvantages, then there is an equity issue, which leads to an ethical problem in this case. So equity is then a commitment to eliminate these air quality disparities and its determinants, so that we make sure that people who are disadvantaged, either economically, socially, or environmentally, they are not disproportionately burdened with air quality risk. And some of the equity targets relate to, like I was mentioning earlier, fair distribution of burdens and benefits, and fair allocation of the opportunity to air quality resources, when air quality resources are available, does everyone have the chance to access those resources? Okay, and then the adverse effects, of course, the adverse effects of air quality, we are seeing that some populations can be able to withstand high levels of exposure because of the capability that they have available to themselves. Another consideration is participation in decision-making processes that relating to air quality. Do we ensure that all sections of the population are involved in the decision-making processes in terms of mitigation efforts to enhance air quality? And that is a key part of it, to make sure that different segments of the population have a say in that decision-making process. So equity, it's really the absence of it's the effort to eliminate or reduce the air quality disparity. Now, the approach that we want to use to expand these ethics is what we call the human capability approach. Now, the human capability approach, it's a concept that underlines a human welfare, and it concentrates or it focuses on the idea that for people to enjoy or to be able to access benefits, we have to look at what individuals or communities or environments are capable of. In other words, we should look at people's capability in reference to air quality resources that we provide to them. And I will use the next couple of slides to unpack this concept a little bit so that it becomes a little bit more clear to everyone. So when we talk about a human capability approach, it encompasses a number of concepts. One of those concepts is resources. So resources, in this case, can be public resources or personal resources. So for instance, when we're talking about resources, air quality resources can be clean energy, could be public transport, it could be parks that allow people to be able to go and enjoy fresh air and things like that. So those are resources that can be provided. And then we also have what we call conversion factors. Conversion factors, they are the contextual individual factors that allow an individual to be able to make use of resources. So for instance, there's a public transport that is there, but for conversion factor, an example of conversion factor is my knowledge of public transport. Do I know that it's there? Do I know I can use it? Do I have the money to use it? Do I have other options? Okay. So for instance, the conversion factors, this workshop, like what we are doing, learning skills for using data and all of that, we know that there is data there. And we now gaining skill sets to now exploit that data and get more insight in that data. That is an example of a conversion factor. So knowledge, skill sets that we gain individually or as a community, they are an example of our conversion factors. So conversion factors make use of the resources. So when we combine conversion factors with resources, then we have what we call capabilities. So with the public transport being there and I have knowledge of it and I have the money to use it, means that it gives me the capability to be mobile, gives me the capability to move. If I know there is clean energy, there is maybe LPG gas I can use for my cooking, that is a resource I know is there. Do I have the money to buy it? Do I have the resources to use it? Do I have the knowledge to how to use it? That will create for me a capability. Okay, so this capability then provides what we call a subset of the capabilities, what we call functionings. Now, functioning for individuals or for communities, all the capabilities you have, you may not get to use all of them every day. Because you're not able to use all of them every day, what we call functioning is the ones you actually get to use. For instance, there is a clean energy that is there. If I do not use it, I have the capability to use it, but if I don't get to use it, it does not become part of my functionings. If I then engage and use it, then becomes my functionings. So a function is a subset of capabilities. Now, the reason why these concepts are very important is that when we are talking about ethical considerations, the capability of individuals is very important for us to assess how ethical air quality is for individuals, for communities, and for certain societies. So this is the framework, this is air quality or ethical framework that is based on a human capability approach, where we will have air quality resources, will be private and public resources, and there could be activity locations, activities that individuals want to engage in. Maybe you want to be mobile, you want to travel by using public transport, or you want to use private transport. So all of these are resources. Then the conversion factors is the extent to which you can use those resources. And those combination of resources and conversion factors will give us what we call the capabilities. And a subset of the capabilities is the functions, the ones you actually get to use. And all of that will create for us what we call a well-being. In other words, your a human well-being in this case. Now, there are several other ethical and equity implications that we want to consider very briefly. So, for instance, there are cases of disproportionate exposure to air quality, which we mentioned earlier, and then also economic impact and energy poverty. For instance, people who rely on dirty fuel for cooking or for other energy services will be exposed to higher levels of air quality burden in this case. Some sources of air quality, which has already been listed earlier, but I would just want to mention them very carefully and relates in terms of their significance in terms of overall air quality. So transportation is a huge part of air pollution, and other sources also come from industrial emissions in terms of power plants, manufacturing, in terms of metal smelters and cement factories and other industrial manufacturing resources in this case. And of course, also household, as we mentioned, indoor air pollution is also a huge one. So household air pollution is a big one as well. People using a biomass, charcoal, wood for energy. And also in terms of agriculture, burning residues, natural resources as natural sources of air pollution. For instance, the Harmattan season brings a lot of, the dust around. And then urbanization effects, manufacturing, transportation, because urbanization brings all of these transportation, manufacturing industries. They are tightly linked together to air quality deterioration. So in terms of air quality or key sources of air pollution, this is the global key sources that have been listed from 1990 to 2020. And what I want to draw you what I want to draw your attention to is the contribution levels. So sources from electricity and heat has the largest, followed by transport, followed by manufacturing, and then agriculture in that order. This is for the entire greenhouse gas emissions by sector. Now, the next one I show here is specifically for Ghana for 2020. And for Ghana for 2020 in terms of CO2 on the top left here, and then the bottom right is for the per capita for greenhouse emissions. What I want to emphasize here is that the major contributors here for Ghana is transport, electricity and heat, and then manufacturing, and then we have buildings and then the other ones. Obviously, vegetation serves as a sink in this case, so it's not a source. And then for greenhouse gas emissions, the top one is agriculture, followed by transport, electricity, and heat. Now, what I want to point out here is some of the top emitters here: electricity and heat, transport, waste is also in there as well. So those are some of the key sources we want to also look at. And then for CO2 emissions, a key part I want to also emphasize on here is the trajectory from 1990 to 2020. What I want to point out here is that if you look at transport seems to be increasing, and this is mainly associated with urbanization. So transport and electricity and manufacturing, these are urbanization related activities. And as urbanization continues, this trend, if not checked, will continue to be the big emitters or the big sources of air pollution, which is very, very key. I want to use the example within the COVID era to illustrate the impact on transport. So when the COVID happened, there are a number of, for instance, lockdown and other things that were implemented. So here on the bottom left, what I'm showing here is the spread of COVID in Ghana. It started in Accra and then it went to Kumasi in Ashanti region, and then it's expanded to the rest of the country. So we're just using an animation to show how it spreads. But on the right-hand side of the plot here, what we've shown here is when the lockdown was implemented in I think in March, no, early April or something, 2020, we have here on the top right, it's the typical traffic in Accra. So this is the typical traffic in Accra, where we are having the orange and brown colors that indicate high traffic. And then the green ones means less vehicular traffic in this case. And then on the bottom, what we see here, it's Monday, 6 April 2020, 6 p.m. 6 p.m. This is for evening traffic. So because of the lockdown effect, what we see is that there's less vehicular traffic. And so we see a lot of green, the roads are indicated with green colored lines, means that there's less traffic. So what it means is that the lockdown has significantly reduced vehicular traffic on the road in Accra. So we use this data to exploit the air quality within that period. So we use the data from Sentinel-5, the precursor from the ESA data. This is looking at only carbon monoxide. So before the lockdown is what we see here on the top left with a red plot here. So it's showing the level of CO, carbon monoxide, before the lockdown, and then after the lockdown is the chart we are showing here at the bottom right. So we are seeing about 31% reduction overall in CO during the COVID time, just in terms of reduction in vehicular traffic. And we do a similar one for nitrogen dioxide. And with nitrogen dioxide, what we see here on the top left, it's before the lockdown. And then after the lockdown is what we are plotting here at the bottom right. So here, there's about 38% reduction in nitrogen dioxide. But what we see in the red, in the bottom right, what we see in the red one there, it's around the thermal-industrial area where the lockdown did not limit the industrial activity. So the industrial activity continued to go on. So we see the red one line, or the high level of nitrogen dioxide still around during the lockdown as well. So these two results really demonstrate how public transport interventions, for instance, can lead to significant reduction in air quality or air pollution in general. Now, another impact result we want to really emphasize here is the impact of urbanization. We know that the world global population is increasing. So what I am plotting here is the share of the total population who are living in urban areas at the top left, and globally, high income, upper middle income countries, Ghana shown there as well, middle income countries, low income. The population is increasing in terms of those who are living in urban areas. It means urbanization is increasing, more people are living in urban areas. And the same plot is being shown at the bottom right as here as well. Specifically for Ghana, what we see here is that the urban population overtook the rural population around 2009. So we see the crossing over. So that has continued to increase. Now, the linkage of this excessive urban growth in terms of air quality is what I want to relate to in terms of inequality. How some of these urbanization is leading to increased inequality, and increased inequality means higher levels of ethical air quality, ethical issues. So on the top left, what I have here is the plot of the percentage share of urbanized areas on the vertical axis, and then on the horizontal axis is the GDP. The GDP obviously indicate higher GDP means the economy is very strong. Lower GDP means the economy is very weak. So Ghana is located just around there, and our urbanization level is about just over 60%, but our GDP is quite low. So higher GDP, like as I indicated, it's really good. So for instance, countries like, for instance, maybe Brazil there, United States, Germany, Japan, they have quite higher high levels of GDP, and most higher urbanization also means that you need a higher GDP to be able to combat air quality challenges. And on the bottom right, what I am showing here is what we call the Gini coefficient. The Gini coefficient is an indicator of disparity. So high disparity means that people living in that society are very, very different. If the Gini coefficient is very low, it means that everyone is very similar in terms of economic income in this case. So Ghana's Gini index is about 0.4. It's about 0.44, just below 0.45. And our Gini GDP, as indicated here, is just close to 5,000 indicated there. So what this is indicating is that there is a high disparity in terms of Gini coefficient, which is 0.44. And we need a higher level of income to be able to combat that. And the argument I am trying to propose here is that we have a high level of urbanization, but that does not correspond to a high level of GDP, which is a problem in terms of combating air quality challenges in this case. So, in summary, key point I'd like to leave with you is that air pollution is a silent killer, as we have illustrated in terms of respiratory disease and cardiovascular related illness as well. And that air quality can be enhanced as indicated in the COVID example. And while also noting that urban growth is very important for development, it can also lead to equity, ethical issues in terms of air quality if we have not had enough economic development to be able to combat those pollution levels. And that rapid urbanization actually increases inequity, which leads to air quality disparities, which also raises the question of equity or social justice implications. So we need to balance urban growth with equitable and ethical air quality consideration in this case. So some take-home messages is that we need to investigate disparities in air quality, and as with some of the data analysis that you've been carrying out in the previous session, shows that you are gaining skill set to be able to understand disparities in terms of space, in terms of time as well. And also to promote ethical air quality policies, clean energy, public transport, or clean public transport, and related policies. And we also need to look at human capability as well. So that policies that we are advancing, we need to look at it in terms of the capability of individuals, the capability of communities, and then the capability of the environment. And very importantly, structural changes needs to also happen. Some examples are listed here. Clean energy for cooking, for transport, for industries, and public transport as well. And in terms of the various interests in air quality, we need to balance scientific integrity with public health, environmental, and economic interests. With that, I leave you with this. The talk can be accessed online by scanning the QR code there, but I'm happy to take questions and comments and other discussions that you want to have on this. So thank you very much.
Thank you so much, Prof. I think we can do better for Prof.
Thank you.
So please, at this moment, if we have any questions, suggestions, or comments.
Thank you very much, Prof. Kwabena Fusuamankwa from CK Tadem University Nevrongo. My question is on a graph that you did show about the various sources of pollutants in Ghana. And looking at that, I realized that transboundary transport were not captured. Is it because perhaps you don't have better inventory on it, or it wasn't just looked at?
Okay. Thank you very much. Please, were you referring to this slide so that I can go to the exact one? Is it this one?
If you can show it, there was a slide that was talking about the various sources of pollutants to
right.
That has been
this
captured.
one?
It's not showing. We're seeing you. So if you can show the slide, I think you had the.
This one?
The earlier, the first one you did. Yeah, this one. No. The other one. Oh, come. The other.
Oh, is it this one?
Exactly. Yeah.
Oh, okay. So this is a global data. So, for instance, transports, all aspect of transport is included in terms of road transport, in terms of water transport and related. So, and then when it comes to manufacturing, you know, it's included a whole broad range. So because this is a global data, there is a lot of smoothing in the data as well, because the industries, as far as they have been classified under, for instance, transport, they are included. So transport here will include transboundary transport as well as urban transport in this case.
I'm looking at, for example, transboundary transport. When you are looking at Sahara, that's traveling down to our area or maybe proceeding to Europe and Asia.
Oh, right. Yes, that will also be included because, so for instance, if you, the inventory in this case will be reported at a national level. So for instance, if somebody is traveling from Ghana to Nigeria by bus, for instance, so if the inventory is taken at the Ghana side of things, that will be accounted as a Ghana data in this case. But I understand the issue. There will be some uncertainties in this case in terms of transboundaries, whether there will be a double reporting, for instance, whether it will be reported in Nigeria as well as reported in Ghana. So I understand that could be a data uncertainty in that aspect. Is that a question that is that a challenge that you're referring to?
Yeah, Prophet, it's okay. It's okay, thank you.
All right.
And please, those online, you can send your questions in the chat box.
Thank you very much, Prof. Gift. I think for me, my name is Sheikh Sharif. I'm from Liberia, from the United Methodist University. And I think I had a very good insight from your presentation and lots of take-home messages. But I have two questions, or let me say concerns, that I will just need some clarity on. I saw the presentation, I saw your explanation and data-driven analysis on the CO2 and nitrogen dioxide and especially including carbon monoxide, especially before the COVID and after the COVID. But my question is, the first one is, how do you tend to address these scenarios in the medium and long term, of course, not the short term, especially with trans-border issues? The question comes to mind, take for example, you have, for example, half a scene that is just across the Ivory Coast border. You know, you have these nice measurement parameters. You are trying to take note about how the pollutants are maybe in that region, especially for industrial areas. But then how do you control that on the side of Ivory Coast? I mean, you are doing all of this trying to improve, limiting the exhaustion or the proliferation of this gas across through your monitoring and, I mean, integrating different policies across different sectors. But what happens if that is not done in the Côte d'Ivoire area? Because this has no jurisdiction. Like the oceans, the air crosses borders and they affect the residents. So the local actors or citizens are the ones that suffer the most. But what happens to the policy integration or harmonization across these two states? And lastly, my second question has to do with from your take-home message slide, you talk about balance. And the reason I say this, when you talk about balance, and initially during the your presentation, you were keen on having similar balance, but between public health, environmental, and the economic interests, which means government should see reasons for sustainability and not just granting licenses to the industrial complex to keep on polluting the environment. There should be some balance there. But you mentioned something about scientific integrity. That comes to mind. It said that the academic setup is not reporting transparently on these issues or trying to polish it, or because when you say scientific integrity for the balance with these the three contexts, public health, environmental, and economic interest, then something from the academic environment has not been done properly to support these different actions or initiatives locally, regionally, and internationally. Thank you very much.
Okay, thank you very much for your question. Yeah, so these questions are I think it's more of a discussion in this case, and I will try and respond to your question. They are really, first, the boundary effect. So a boundary effect is real, and it affects, we're talking about air quality, which does not respect boundaries. And we have sources and we have circulation that will, once the air pollution is there, the circulation will take over it, and atmosphere impact will also take over it and as well. So there is a boundary issue that we have to resolve in terms of air quality. So and I think when it comes to this aspect, this is where the scientific community, it's very important to have a broader understanding of air pollution so that it's not just from the local, we don't have to understand it from the local point of view only, but from the global point of view. So this is one scientific investigation. It requires that, but it also requires, as you pointed out, transboundary collaboration and partnership, and also transparency in terms of the data, so that different countries can see the data and be able to forge some collaborative solution going forward. But obviously, it can it needs to be underpinned by data and then cooperation. So that's what I will say to that effect. And another aspect I want to mention with this is that it also requires very detailed local monitoring, plus together with satellites, regional level monitoring, so that we can, validate some of those global data with, local data to be able to get much more accurate information. So that is that part. That's what I would say. But like I said, that is very much open for discussion as well. Then your other question about the balance, and I totally agree in terms of the balance. Yes. I have pointed out earlier about the dilemmas that air quality professionals can actually encounter. The pressures are real if you are working with people with economic interests, if you are working with people with environmental interests. So the pressures will be coming from perhaps, some industries who have serious economic interests, and they can also influence academic people as well. So that dilemma, I think it's real, and part of making the air quality data open and transparent is to be able to address this scientific integrity, so that we can find out where certain regulations are coming from, what data underpins that, so that people can openly, address that. I hope I may have addressed your question, but thank you for raising the question. Thank you. Cheers.
Thank you, Prof, for your presentation. I think it's been a good time listening to the ethical considerations when it comes to air quality in this part of the world where we find ourselves. I have a few questions. Maybe I start off with the first one. What I wanted to ask you is that is air pollution. Okay, let me take it from this angle. How should policymakers, especially in developing countries like Ghana, balance economic growth with air quality regulations? Do you think that it is ethical to relax air quality standards to boost industries, since I mean most developing countries are having a toll on the economy? And so do you think it is ethical for us to at least relax the standards so that we have more industries and that will create more jobs? That's my first question. Can I give you the second one?
Yes, please go ahead.
Okay. So my second question, I think, is a bit related also. Is it ethical for the developed nations, okay, to outsource, pollution-heavy industries to developing countries? What I'm asking is that when we go out and ask countries to come and invest, especially in Africa, do you think it's ethical for them to bring in industries that, have heavy pollution or emissions? Okay. And then finally, the next one talks about the communities where these industries are located. Do you think that the local residents should have a say in whether these polluting industries are brought to operate near them? What is your take? Communities are there before you realize cement factory is brought into a community. Do they have any say in the location of these kind of industries, or it is just left with the decision makers to decide where to place these heavy polluting industries? Thank you.
All right. Thank you very much for your question. Obviously, I really enjoy all of these questions because there is no, well, from my side of things, it's more of a discussion question and quite engaging. So I'm very happy to engage with these questions and give my thoughts on it. So yeah, thank you very much again. So if you don't mind, I might start with your third question first. So the question of whether local residents should be involved in a decision-making process. And absolutely, that is part of what we are saying in the what is it, the ethical yes, widening participation in the decision-making process. So local residents should be involved. It is not ethical if they are excluded. It is not ethical if they are excluded because they are key stakeholders. The project will affect them. So they are very, very important. They should be they should be on the decision-making table. So that is the number 3. I'll then take your question number 2. Rich countries exporting their polluting industries into poor countries like Ghana, for instance, or yes, and that is unethical. And having said that, already in terms of air quality, we also know that air quality is a global phenomenon. Even what is air quality in Asia can affect what happens in Ghana, in Africa. So there is a global circulation. We have to understand that. So air quality, so for already rich countries are already polluting very heavily compared to our Ghanaian industries. So for them to export their industry to come to Ghana and operate, it is one, unethical. But I will also say this is where our local air quality professionals and our local governments and our national governments have to be be informed and balance the economic interests and the health interest here. So I think a key aspect with my presentation, a key aspect was the public health. Air quality is a human health issue. It's an environmental health issue. It's a biodiversity issue. So the damage is very, very diverse and very, very severe. So it is unethical for that to happen. Number one, your first question, which is Ghana, a country like Ghana, how can we grow by balancing economic growth with stringent air quality standards? So here, the word here is balance. I will give you an example about the COVID time. See, during the COVID time, people know that it's very risky to go out and be interacting, right? People know that. But they also know that if they stay at home and they don't have economic power to buy food and things like that, it is also very, very dangerous. Now, the reason why I'm bringing this is that there has to be the word balance. It's something that we have to work with to look at people's livelihood as well as environmental and human health. Because sometimes humans will know the risk, will know the medical risk is there, but we are willing to take the risk. So I will say that we need to balance the livelihood part with the livelihood part with environmental protection. So that balance, it's something that we should all contribute to that discussion in terms of what that balance should be. All right, because you can have excellent air quality, but your productivity or your may not be sustainable because you don't have the capital to continue that environmental protection. So it's a conversation we should all engage in to find that balance, what that balance will be. So thank you. That will be my response to your question.
All right, Prof. I think due to time, our next session is supposed to start at 11:30. We would want to take a short break for coffee before the next session starts. So we would like to thank you so much. We can continue the conversation in the WhatsApp group. If anybody has any comments or question, I think we can follow up from there. So thank you so much, Prof, for your time. We've learned a lot.
All right, thank you so much too, and for your audience as well.
Yes, so he's part of the WhatsApp group. He's there, yeah. Okay, so coffee is ready. We have 23 minutes, let's say 20 minutes for coffee. Dance session will start at exactly 11:30, please. Yep, so we can start now. Hi, Dan, can you hear me?
Yeah, I hear you.
Okay, great. So Dan will be facilitating the next session. He is Dr. Dan Westervelt at the Columbia University, US. The next section, his session will be on data correction, applying various methods of data correction ranging from linear corrections to ML algorithms. Dan is an associate research professor at the Lamont Doherty Earth Observatory at the Columbia University. He's an affiliate faculty member of the Columbia University Data Science Institute, a scientist with the NASA Goddard Institute for Space Studies and an air pollution advisor to the US State Department. His current research spans from air quality and climate modeling to the deployment and calibration of low-cost sensors for air quality. Before his faculty position at LDEO, he worked as an associate research scientist and a space science, technology, and environmental policy postdoctoral research associate at Princeton University. Dan, please welcome, and then over to you.
Great, thank you. Hopefully everyone can hear me okay. Thanks for having me today. I apologize that I'm not with you in person. I've been seeing all the great photos on the Afri-SET LinkedIn, and it's giving me some sadness that I'm not there with you all in person. But hopefully this can be a good session. I'll start by just sharing my screen. Hopefully this is coming through. What I wanted to do is just put up the data link for this tutorial really quick. I think I sent this yesterday, and I think it's been sent before, but just in case you haven't got it yet, this is the last chance. The data for this tutorial is at this link right here. So you can just copy it down really quick. The paper that there's a publication that we did that uses this data that you can see right there. You can take a picture of this if you need to. And then I also have some kind of tutorials for your own pace at this website below, which I can send you all later so that you don't have to take it right now. All right, so hopefully everybody got a chance to get that data. I'm going to stop the screen share for this and let's look at the data really quick. So give me 2 seconds here. Okay, so if you have the data, you should be able to see a folder that looks something like this. It has a handful of files and a couple of folders. And so the data is in two formats here. We have the first one, which is this CSV file. So this is PM 2.5 data from Accra at the US Embassy in Accra. So this data is publicly available. You can go online and get it. It's very easy to obtain. But that's one data set that we're going to be looking at. So you should be seeing it sort of on my screen right now. It is like I said, data from the U.S. Embassy. It's using a BAM 1020 air quality monitor for PM 2.5. It's a reference monitor, so it's like what also similar to what is available at Afri-SET, where you all are. And it's a monitor that is certified by various authorities to attest to its accuracy and ability to uh, give you high quality data for PM 2.5. So it's a trustworthy source. And the data format kind of looks something like this. You have kind of the spreadsheet with the dates. So there's some columns for the dates, sorry. And then there's columns for concentration. So we're going to specifically be looking at the raw concentration. You'll notice that some of these values at the top here are negative. So these are invalid data. If you look at the QC quality control, it says invalid data. We're going to start taking the data from about March. So this is, if you look at the dates, I scroll down here. Sorry, bear with me for 1 second. The data around here is March 1st, so 2020, March 01. That's when we're going to start taking the data. This has got a valid quality control. It has the concentration is right here in this column, 48, the unit microgram per meter cube. So we're going to start taking that data. But we're going to eventually we're going to start using some Python code to do this, but it's always good to look at your data before you get started, just to know what format it's in so you can figure out how to approach loading it in and cleaning it and working with it. So that's one data set. That's the U.S. Embassy data set. The other data set comes in this, it should come in this zip file called AQM. And if you unzip it, you'll get this folder that has a bunch of different files. And so what these files are purple air data. Okay, so purple air is a type of low-cost sensor, similar to the air gradients that you guys.
Hi, Dan.
Yes. Yeah.
Yes, sorry to interrupt. Could you please zoom in a bit? It's
Okay.
it's hard to follow.
Yeah. Yeah. Okay. I'll try. I'm not sure how to do that, but let's see. Here we go. Maybe this will help. Okay, maybe that's a little bit better. This part's not super important anyway. I just what the folder just you'll have a similar folder on your computer and it'll have these a bunch of different files. It'll have .csv files and .log files. We don't really care about the um, the log files. We just care about the .csv files, and you'll see that the file names have dates on them. So the first one I have is 2020-03-02, which is March 2nd, 2020, and it'll go down all the way to about end of or beginning of September, so 2020-09-04. So if you look at these data, let me just switch this back. If you look at these data, and okay, for this one I can zoom in. So there we go. Hopefully that's a little bigger. What we're seeing here now is purple air data. So this is the low cost sensor data, similar to the air gradient. There's a bunch of columns here. A lot of them don't really matter as much to us. You'll see here there's the date time. So this is the UTC date time, so universal time. It has the month, day, year, the letter T, and then the coordinates, or sorry, the time listed there with a Z at the end. So it looks like there's data every 2 minutes. So you have 12:16, 12:18, 12:20, 12:22, 12:24, so on. So there's data every 2 minutes, and maybe we didn't emphasize this on the previous data set, but it had data every 1 hour. All right, so there's going to have to be some harmonization here, averaging up the data into 1 hour from the purple air. All right, so there's a bunch of different columns here. The ones that are going to be the most important are actually right here on the screen, the temperature and the humidity. We're going to use that for some correction factor development. And then the other column that's important is the PM 2.5 measurement itself. All right, so purple air has a lot of different columns here. And for PM, and the one that you want to use most often is this PM 2.5 underscore ATM. That's the values that, or the quantities that they recommend for outdoor air quality studies. So all these other ones here, PM1, PM10, PM1, don't worry about those. We're going to use this PM 2.5 ATM. There's a bunch of other stuff here again. One thing that's unique about the purple air is that it has 2 sensors for measuring optically the particle counts. So if you looked at the air gradient, or also if you looked at kind of Teddy's do-it-yourself air quality monitors, you probably had these little blue square rectangular thingings that those are actually the optical particle sensor. The purple air shoves 2 of those into its housing. And so there's going to be kind of like redundant information that we can use to average together to get a more accurate reading. So what we'll do is we'll average the column here, the PM 2.5 ATM. That's the channel A PM. And then we'll also, if you scroll over here, you'll notice that there's a repeat of these column names, where here it says PM 2.5 ATM B. All right, so this is the second plan tower sensor. So we're just going to average those 2 together, long story short. But they have, sort of this redundant system so that if one goes down, the other can work. Also, so you can assess the performance by comparing the 2 sensors. But yeah, just a little note on that. Okay, so that's sort of just looking at the data. Now that we kind of look at the data, we can actually start to do the programming. So I think you guys have already been sensitized to Anaconda Python. So that's the tool that we're going to be using. In particular, I'm going to be using Jupyter Notebooks. So if I go into Anaconda Python and I launch my Jupyter Notebooks, I will make this larger for you in 1 second. Let me just pull up the document. What I'm going to do is I'm going to open that file that I had shared with you. So in the data, there was a Jupyter Notebook file called ipynb.ipynb. And what I'm going to do is I'm going to find that file on my system. I'm going to open it up. It'll look a little bit different on your system based on what you have, but now let me zoom in here. Let's see. There we go. So hopefully that's a little bit more visible. You should see a file that looks something like this. mlr_correction_python.ipynb. Also in that folder, you'll notice I have those files that we just looked at, the CSV files. All right, so I have this one, Accra PM 2.5 2020 YTD, that's the US Embassy reference data. And then I have a folder with all those AQM files. All right, so these are the ones that we just looked at. So the code that actually does the work for you is right here, this mlr_correction_python. So you have this for your reference. We're going to go over it in more detail, but this is sort of, it does everything. I also have the version of this in R. We're mostly focusing on Python, so I'm not going to go over the R one, but it's in there if you want to look at it, and you can see it's very similar to what we're going to be doing in Python. Okay, so you have the code here, this Anaconda Python file, sorry, this Python Jupyter Notebook file. What I want to do instead, though, is open up a new one, all right, so that we can go over it kind of in real time. So if you're in your Jupyter Notebooks, you should go to New Notebook, sorry, and just get yourself a blank notebook. We're going to use the Python 3 kernel, and now we are free to code here. So I'm operating under the assumption that everyone has this week gotten used to using Jupyter Notebooks. They've seen some great presentations from various Afri-SET team members on this. So hopefully this is a little bit of a review at times, and just as a heads up, if you have trouble following along in real time, I do have to go somewhat quickly because we are limited on time. But if you have some trouble following along, there will be recordings of this. It's being recorded, so you'll be able to access what you need. Okay, so what we're going to do first is import a bunch of things. All right, so they probably explained that in Python you have the base code, but you also have a bunch of libraries and packages that, yeah, sorry, question?
Yes, so this is Wig. We are trying to follow, but it's quite difficult. You are going a bit too fast. So
Okay.
let me just check if everybody has opened the code or the script.
Sure.
So we can follow through.
Sure. I'll stand by for your go ahead.
Okay, so please, do we all have it open, the script, so he can proceed? Okay, Dan.
Good?
Yes, so please, you can go ahead, but then.
Okay. What's the stopping time? Is it 12:30 for lunch?
1.
1. Okay, good. Okay, so you have the script open that let's name it something. So at the top you can change the names of the file. So we can just name this MLR practice. It's always good to save. And then the first thing I want to do is import a bunch of things. So I have to import the various libraries. I I have them already kind of saved. What I might recommend is that you copy and paste them over from the code that I provided just to save time. All right, so here's the code that I provided. Here's the file that we're working on. So while I leave this up, there's a few things, here. One is this thing called Pandas. Pandas is a kind of data analysis tool. There's something called date time, which is just an easy way for Python to work with dates and times. As you can imagine, we are going to be working with dates and times since we're working with time series air quality data. The next few ones here are related to the sklearn, scikit-learn package in Python, which allows you to do statistical modeling, um, things like linear regression. It also lets you do various machine learning type of approaches as well. The one down here, matplotlib, this is a plotting feature in Python. So it allows you to plot the data, which we want to look at. And then the last one, glob, is just something that allows you to access your files on your computer. So we're going to import all those. We execute that line of code. You can execute it by pressing the play button, this little triangle, or you can hold shift and press enter within the cell. And then the first thing we're going to do is load the CSV files. All right. And actually, even before that, what I'm going to do is I'm going to dump out all the file names and unpack them into what's called a pandas series. All right. So you remember the purple air data, there were files for every single day between March and September. So I want to put all those in a list so that I can loop through them and load them all at once instead of issuing, 6 months worth of load commands. So I'll call this purple file because it's the purple air files. And what I'm going to do is create a pandas series. Hopefully some folks have explained pandas already. But the way that you do that is just by creating the series, then you use the globe or glob package, and then you give it the location of where the data lives. All right. So for me, it's in the current directory I'm in, one further down from that current directory called AQM. And then I want to take all the CSV files. So this star here means it's a placeholder that says, look for all the files that end in .csv. All right, so let me back up a little. Let's go here. So the directory I'm currently in is the directory that has my code. All right, so let me refresh this. Do I need to save it? Why is it not? Okay, so I need to move this this file here to the right directory. All right, so I want it to be in this directory where I have the data. Okay, so if I have the data, then if I put my code within that directory, then I can easily access the data without having to give the full path. All right, because otherwise I would need to write the full path here. And I don't want to do that. I just want to use these shortcuts. So this dot means the dot is sort of an abbreviation for use the directory that you're currently in. And then after that, you can reference further directories. So I'm telling it to look in the directory I'm currently in, which is right here on my screen. And I'm saying go into the AQM folder, which is right here. And I'm saying take all the CSV files. All right. Now I need to do a little bit of housekeeping. So bear with me for just a second here. What I'm going to do is just create this new notebook. And so I'll just copy over the stuff. So don't worry about this part. This is just me doing some housekeeping on my end. We'll copy this over. I will work from here. Oops, forgot to parentheses. All right, and then I'm going to rename this to MLR practice, as we had done. Now, if I refresh, okay, now you can see that we have the file that I'm working on in this directory. All right, this MLR practice. This is the one that I just created. Where did it go? All right, let's close it and let me try to reopen it here. It seems to have disappeared. All right. 2 seconds as I re-enter the information. Bear with me here. Now let's save it. All right. Now we should be good. So yeah, I have this file here. Now it has the information I want. It's got the stuff. All right, so we're good. You can, so I put it in this file, in this directory again, so that we can easily access the data. Ultimately, it's not that important. It just depends on how you reference your directories. All right. So I'm telling it to, with this line here, I'm telling it to look for data in the current directory that this code exists in, and then one directory beyond that called AQM. Okay, so on the screen right now is the directory that the code exists in, and then the next directory beyond that is this AQM, and that's where the data is. All right, so that has to match in your code. Okay, so if we then just print out the elements of this series, we should get all the names of the CSVs. All right, for some reason it orders them randomly instead of like chronologically, but that's okay. You can see that there's 187 total files, where there's some CSV file for a given day. Okay, the next thing we want to do is we want to create a list of the columns that we want to import from these purple air files. Because you remember there were all kinds of different files, all kinds of different columns, and we don't want them all. So what I'm going to do is just create a list called imp column for import column. And I'm just going to list the names of the columns that I want. All right, so I want the date time. We can reference here, which is, again, you can always go back to your data and you can open up and you can look. Let me zoom in. You can look at what columns you want. So I want UTC date time. Obviously, we need that. I'm going to want temperature, humidity, so we're going to list that. And then, of course, I want the PM 2.5. Where'd it go? This one. So I want that column as well. So we're just going to go through here and list some of these columns. UTC date time. That's one of the most important ones. PM 2.5 ATM. That's the PM 2.5 values. Remember, there's a second channel or a second sensor. So we're going to say, give me PM 2.5 ATMB as well. We're going to end up averaging those. And then the rest of the columns that I want to isolate are going to be weather related, basically. So I want the temperature, current temp F. I want the relative humidity, which is called current humidity. I could actually stop there, but just for this code to be consistent with what it is online, I'm also going to import the dew point and the atmospheric pressure. We're actually probably not going to use those, but I just want to be consistent. So I close this list here with a square bracket, and I execute that line of code. And then simply what I'm going to do is start the process of loading the data into Python just for these specific columns. Okay, so I'm going to make what's called a pandas data frame called purple. I think you guys have probably used pandas in previous lectures. But I'm going to create this pandas data frame. It's just going to be empty at first, but we're going to fill it up. We're going to tell it to have the columns that we just listed. All right. So if I do that and I just say, okay, give me this data frame called purple, right now it'll be empty. So if you see the output, it just says, it has my columns that I asked for, but there's no data in them. So to get the data, we need to use the pandas read underscore CSV command. All right, read CSV. That's what gives you the sort of ability to take this data and bring it into Python, into your Jupyter notebook. And what we want to do is we want to loop through all the files. Okay, so we have all these files for the purple air. We want all of them, and we don't want to load them all at once. We don't want to say like, this would be really bad code to say like file 1 equals, and then say pd.read CSV. You would put the file name like 2020/08/01.csv, blah blah blah. We don't want to do that because that would be, and then you would go file 2, dot 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 2020/08/02.csv. That would be really repetitive. So what we're going to do, instead is loop through. And that's why we created this series here of file names so that we can loop through them. Okay, so we're going to say for some arbitrary looping variable, which I'm going to call I, in the series purple file. Okay, so for I in purple file. So purple file, we remember, is the file names for all the purple air data. We can simply say that we want to read CSV of this index I, all right? Because that I is a stand-in for all of the file names in that list. And then we're going to say use columns, use calls imp column, because we want to use those same columns that we defined. And then what we're going to do is fill in our data frame. Okay, so we created this empty data frame right here in cell 7 called purple. We want to fill it in with what we're loading. All right, so we're going to use something in pandas called the concat. And what we're going to do is tell it to concatenate whatever you already put together in this purple data frame, concatenate that with each new file that you load. And I'm going to tell it to ignore index for now. We just want to get all the data in there. We don't really care about the index. So if I load that, you might get a warning like this. Don't worry about it. As long as it doesn't say like error, then it's okay. Right now it just says future warning. That's okay. We don't worry about that. So if I look at purple, now, as previously it was this empty data frame, not very good. Now it's a data frame that has data. Okay, so you can see it's here. All the columns are not shown. Sorry, all the rows are not shown because there would be a lot of data. But you can sort of get the idea here, that we have all kinds of dates and times, and the PM levels, the temperature, humidity, these other ones that we don't care as much about, but we have them in there anyway. Um,
Hi, Dan.
yep,
Yes. Can you hold on a minute as they are trying to catch up?
sure. I'll wait for your go ahead.
Hi, Dan.
Yep, are we ready?
Yes, we are.
Okay, thank you. Yeah, like I said, we will have this recorded. So if you're not able to keep up exactly, don't worry too much. All right, so you have this data set. One thing I want to do right off the bat is I want to remove some invalid values. So you can't actually see them in this in this preview of the data right here on my screen, but there's going to be some values that are what we call NaNs, non-numbers. So I want to go ahead and just remove those. So I say I use the dot drop NA, so it drops the not a number data. And then if I just print that out again, I'm going to see a very similar thing. You can see that previously we had 133,843 times or rows. So each row is a time. And after dropping the bad data, we have 130,835. So we didn't actually delete that much data, just a few points. Okay, the next thing I want to do is it's always a good idea to just look at your data, visualize it. So we're looking at it right now in a table, but that's not as useful as sort of a graphic. So I'm going to use the pandas plotting tool. So every pandas data frame, you can just add a dot plot to it, and it will allow you to make a plot. You just have to tell it what you want to be your x-axis and your y-axis. So I want to make a plot of purple air PM 2.5 concentration on the y-axis versus time on the x-axis. All right, so I'm going to tell it that my x values are UTC date time. My y values are, for simplicity, we'll just do the single channel PM 2.5 ATM. There's some other features you can do here. We can change how we want the data to be displayed. So I want it to be dots. So I'm going to say marker equals dot. And then line style, none. I don't want it to draw lines because it's going to look kind of chaotic. So if I do that, you can see you get this plot. Obviously, this plot is a little bit ugly. The x-axis has all the dates mashed and mushed together. We don't like that. That's not very useful. But this can at least just give you a rough idea of what's going on here. All right, so you can at least see, you know, the peaks, the high concentrations. So this y-axis is going to be in the micrograms per meter cubed of PM 2.5. So you can see kind of the values. This is just sort of a sanity check to make sure that everything looks normal. And you know, there's not any sort of really kind of strange things. So we'll move on. That's not really that that essential. What I want to do next is I want to change these dates. All right, you can see these dates here are kind of messy, and we wanted to get it into a nice form. So what we're going to do is convert the date time into something that Pandas Python can use a little more clearly. Okay, so I'm going to tell it, take this column in my data frame, UTC date time. That's my original column. That's what's viewed here on the x-axis. And I'm going to convert it to a different format. All right, so I'm going to use the pandas 2 date time. And I'm going to convert it. I'm just gonna simply rename it. So, or sorry, I'm gonna overwrite what's there. All right. So by doing this, I'm telling it take the old purple UTC date time. So take this kind of garbled nonsense and convert it to something else, but give it the same name. So basically, just overwrite what was there already. Okay. And so I have to give it what format I want the data in. So for here, you have to use these sort of signifiers. I don't have time to go into kind of all of the details, but what we want to do is we want to tell the code what format should they expect the data in? Okay, so for that, let's go back up here. This is how the date data came to us. It came to us with a year, a slash, a month, a slash, a day, the letter T. It came to us then with hours, minutes, and seconds, and then the letter Z at the end. So we have to tell it that that's the format. And we have to use these sort of like generalized signifiers. So capital Y is for the year. There's my slash. Capital M, or sorry, lowercase m is for the month. There's my slash. And then lowercase d is for the day of the year. Then, of course, there was this T. All right. So you can see 2020, 08, 03. I just sort of generalized that. And then there's the letter T in the middle. And then it starts the hour, minutes, seconds. So we go to capital H for hour, the colon that separates the hour and the minutes, capital M for minutes, another colon that separates minutes and seconds, and capital S for seconds, and then the end has a letter Z. So there's documentation online that tells you like how did I know that capital Y is the year? How did I know that lowercase m? You know, that there's documentation online on pandas for that. So you can review that on your own time. I'm happy to provide links if you're not able to find it. And then I'm also gonna just type this other keyword exact equals false. This might not be necessary, but I just want to protect against the fact that there might be some there might be some random examples of the dates that are not exactly like this format. So you can see the ones that we have in the sample, they're all of that format. You know, they're all the same. But it doesn't mean that somewhere in these 130,000 dates that one of them had some stray character or some corruption or something like that. So just in case, I put exact equals false. And then if I print the data frame again, you should get something very similar, but now our UTC date time is in a nicer format. All right. So now it's got this 2020 08 23, and then the date. There's no T, there's no Z. It's a little bit nicer, and Python can work with this a lot better. All right. Next thing I want to do is I want to subset the data. These files have there might in this data set there might be some files that were for before. If we look at, actually, I might not need to do this. Yeah. What I was going to do is just ensure that all of my CSV files are for the dates that I'm interested in. Making sure there's no stray dates that somehow got into here, because what we're going to do is we're going to look at data from about March to September. And it looks like just browsing through my files here that I'm pretty okay. So I don't need to do anything regarding that. Let's skip that. The next thing that we're going to do is read in the reference monitor data. All right, so we've read in the purple air data. We have it, it's there. Let's set it aside for a second. And let's read in the reference monitor data. So here we don't have to do any sort of looping. We just have the one file. All right, so pd.read CSV, just like we did before. And then the file that I want to give it is Accra PM 2.5 2020 ytd.csv. So where did that come from? again, in the folder that I have my code, this MLR practice, you'll also see that I have this spreadsheet. All right, and it has hourly PM 2.5 data for ACRA from the reference monitor. Okay, we looked at this earlier. So we just want to load that in. And well, sorry, let me go back to the right thing here. So that's the command, just read CSV. We don't have to do any looping. We don't have to do anything fancy here, since it's just one file. I'm going to go back up here, and you can look at the data frame. And so now you should see this data frame kind of similar to the one that we had looked at on the spreadsheet software. You can see there's some NANs, not a numbers, so we'll have to get rid of those in a bit. But let's not worry too much about that now. Let's create a new, sorry. Create a new cell, and we'll go on to the next step. So what I want to do is I want to also convert the dates here into the same format. So we have this kind of date LT value, which is almost what we want. We want it to match what we have for the purple air. All right, so you can see the purple air has 2020, it has year, month, day, hour, minute, second. We almost have that for the US Embassy data. It's year, month, day, hour, minute, and then either PM or AM. So we can convert that pretty easily by using a similar command that we just did. So embassy data, I'm going to create a new column within the embassy data frame called date. And I'm going to use this command that we already experienced a few minutes ago called PD2DateTime. And I'm going to tell it as input, take what the embassy data says for date and convert that into the pandas format. All right, so basically I'm saying create a new column called date and convert it into pandas based on the input of this date parentheses LT, which stands for local time. And you might get a warning. That's okay. I know exactly why that warning comes up. It's nothing to really worry about. But if we look at now that data frame, we should have another, scroll to the very end, it creates a new column called date. And now this date sort of matches the purple air style. All right, so it has hour, minute, month, day, year, hour, minute, second. All right, so we have to get these things to match so that we can work with them simultaneously, side by side. I also need to convert. What I'm going to do is also do the same thing for the purple air data. I had already done this, but I want the purple air data to have the same name for the date. All right, so I'm going to say purple data date. And then I'm going to convert that to date time from what I had previously saved the dates in. Oh, did I not? Oh, sorry, I was calling this Purple. That's right. Yeah. Second. Okay, that works. So what I just did was I created another column called date in the Purple Air file. Or sorry, the Purple Air data frame. And you can see now that it matches the format month, day, year, hour, minute, second, month, day, year, hour, minute, second, which is the same as now in this US Embassy data. We have this date column, month, day, year, hour, minute, second. So we're good there. Everything is aligned and matching, which is what we like. Now, the next thing we need to do is subset the embassy data to align with the Purple Air dates. Okay, so if we look at the embassy data, we have all of 2020. All right, so it starts, let me go up. It starts here, well, not quite all of 2020. It starts at 2020, January 27th is the first day of data we have for the embassy data. And it goes all the way to, at the bottom here, December 31st of 2020. So it gives us basically the whole year. If you recall, the Purple Air data only goes from about March 2nd to September 4th. Okay, so we have to get our embassy data to match that. And so what I'm going to do is just sort of put in a command that does that. So I'm going to say embassy data. I'm going to basically, it's sort of a long line, but I'm going to say just select the embassy data that matches between March 2nd and September 4th. All right, so let me write that in. So this gets a little bit long-winded, so bear with me. So now I'm basically saying, give me the first date. All right, so give me the date you want to start looking at data. And I'm saying, give me everything past that. But then I'm also simultaneously saying, give me everything before the end date. So give me everything past the start date and everything before the end date. And I'm using some sort of Boolean indexing to do that. All right, so now I'm entering the end date. Oops. I seem to have missed a parenthesis somewhere. Hold on one second. Oh, right here. There we go. Now, if I look at the embassy data, it should just be, yeah, you can see it ends on September 4th and it starts at March 2nd. So now it matches our Purple Air data in time. I think I'm going to start moving a little bit more quickly because it's almost lunchtime. So again, you have all the code in front of you in that other file, so you can Maybe if you're having trouble keeping up, just follow along with that code as each step that I'm going, and the steps should match pretty well. And then you can on your own time look at the recording or just practice with the code that I provided. Okay, so the next step is I want to remove the columns that I don't need. So if you look at the embassy data, there's a bunch of columns here that I don't really care about. So what I'm going to do is really all we care about is the date and the concentration in this case. So I'm going to say, give me only the date and the concentration. And I'm also going to say, give me only the concentration data that is greater than 0. All right, just in case there was some bad data, you saw it at the beginning. There was some data that had concentrations less than 0. That is not possible. That would be instrument error. So we want to get rid of that. And so if I do that, those commands here now, you'll see a much smaller data frame. Now we just have date and raw concentration. We got rid of a lot of stuff. And just in case there were any any negative values, we got rid of those as well. I'm not sure if there were in this particular time range, but it's possible. Okay, next step, we need to average the 2 purple air sensors. So you remember there's 2 sensors for PM within a purple air. As we discussed earlier, we're going to average the 2. So I'm going to add a new column to my purple data frame called PM25 average, which is just going to be the mean of PM25 ATM and PM25 ATM underscore B. So this is the second channel. We say take the mean along axis 1, which means average the 2 columns. Okay, and if we look at that, we now have, scroll to the edge, yet another new column called PM25 average. All right, so this is going to be the average of PM25 ATM and PM2.5 ATMB. All right, so right here, this value, 14.5, 14.61, average is 14.555. That seems right. Little sanity check there. Next thing is I'm going to convert the temperature data to degrees Celsius. So the temperature data came in Fahrenheit, current temp F, that means Fahrenheit. So look at these temperatures, Fahrenheit, this is the US temperature scale. This is a US company, so they chose to use that unit. But we don't really like that unit in science, so we're gonna convert it. I'm gonna take a new, yet another new column. I'm gonna create it, and I'm just gonna say, take the Fahrenheit data and convert it to Celsius. So to do that, you subtract 32 degrees. And multiply by 5/9. That's just the conversion between Celsius and Fahrenheit. Get a warning again, don't worry about that. Again, if we look at the purple data, we should now have another column that says temperature C. All right, so this is probably more familiar to you in the audience. Temperature in Accra on August 23rd, 2020 was almost 28 degrees Celsius. In our units, that ends up being 82 Fahrenheit. Don't worry too much about that. But those numbers should be a little bit more familiar to you. The next thing we need to do is what we're going to do is take a daily average. All right, so I mentioned that Purple Air has data every 2 minutes. The Embassy data has data every hour. So at minimum, we need to do hourly averages so that we can match the Purple Air data to the Embassy data. That can certainly be done, and it would be a very simple change from what this code does. But just for simplicity, we're going to convert it into daily averages, and really running out of time here, so I'm going to just copy this over from my code. I'm not using dew point, so I'm going to delete that. What this chunk of code does is it just averages the PM 2.5, the temperature, and the relative humidity. It averages that from 2 minutes to every day. And we have to do the same thing with the Embassy data. The Embassy data comes hourly, but we want it to be every 24 hourly, every day. So I have to do some code there. I'm just going to copy and paste it so that we can get to the next steps. And now if we look at this new, for example, this new data frame called Purple Day, you can see that what we're seeing here now is the daily values for PM. So we have March 2nd, which is when it starts, to September 4th. We have a daily mean PM 2.5, a daily mean temperature, a daily mean relative humidity. Should see something very similar for Embassy Day. We have date and PM 2.5 concentration. So the next thing we're going to do is just merge these two data sets. I want to combine what you're seeing here at the bottom of my screen to what you're now seeing here with all the at the top with this. So basically combine the Purple Air and the Embassy data. All right, so I use the pandas merge command for that. And now we have all of those two data frames that I just showed are now in above in one data frame. All right, so the next thing we could do is simply do a quick plot. All right, so I made a combined data frame called purple_embassy_day, because that sort of says that we take the Purple Air data and the Embassy data and combine it. So what I'm going to do is make a plot from this data frame, purple_embassy_day.plot. I want to make the x-axis my dates, and I'm going to make the y-axis a dual y-axis. We're going to have the Purple Air PM 2.5, and we're also going to have the Embassy PM 2.5. All right, you should get something like this. In blue, we have the Purple Air data. In orange, we have the Embassy data. Now the dates are very nicely formatted from the beginning of March to the beginning of September. And you can see there's, you can now compare the data like in a very easy way, all right? You can see that, okay, the Purple Air data is over predicting the Embassy data in a lot of places here. All right, so the Purple Air data is much higher. The Embassy data is what we would consider as the, the sort of gold standard, the accuracy, the high accuracy. So what we want to do now is basically apply a correction factor to get this purple data closer to the US Embassy data. All right. So to do that, the first thing I'm going to do is I'm going to build a statistical model that can take this side-by-side data and develop some parameters that explain that relationship. All right, so I'm going to do this using just a linear regression. The first thing I want to do, though, is I want to split the sample. I want to split my data into what's called a training data set and a testing data set. So I say train, comma, test. And then I'm going to use this command from Python scikit-learn called train test split. And I'm going to say, look at the data frame purple embassy day. I tell it that the test size data that I want is 20%, and then I have to give it a random state. This can just be any number. Don't worry about the random state. I'm just going to say 70. So what this does is it takes my data that you're seeing on this graph and it splits it 80%, 20%. 80% of the data will be used to develop this correction factor. 20% of the data will be set aside to test this correction factor on an independent, well, somewhat independent data set. Because you don't want to build your machine learning or your linear regression model on the same data that you then test it with. All right, so we do that. And then what we do is we create the model. So we're going to create, I'm going to start with a linear regression model. At this stage, if you wanted to use a different machine learning approach, you could do that. You would just change the model here. And then I'm going to ask, linear regression. I'm going to ask the model to, or I'm going to ask the data to fit a model.fit on the training data. All right, we don't want to use the testing data here, so this is train. And my my x values, my sort of independent variables, are going to be the purple air data, temperature. Let me just make sure that's the right. Yeah, okay, temp is what I called it. And relative humidity. All right, I think probably other folks have explained, why temperature and relative humidity, but those are important parameters for evaluating sensors. So those are my sort of predictor variables, and then my sort of target variable, the thing that I want to sort of emulate and achieve is the embassy data. All right, I want to make this low-cost sensor purple air data close to embassy data. All right. So those two steps do that. There's not really much to output right now, but what we're going to do is we're going to apply this model to the testing data set. All right, so now that was the training data set. Now what we're going to do is create a column in the testing data set called PM 2.5_C for corrected. All right. And we're going to tell it to take the model that we just developed and use these values in the testing data set. We want to use the purple air PM2.5, we want to use the temperature, and we want to use the relative humidity. These are sort of the predictor values, all right? So this would be just for, like I said, just for the testing data set. For plotting purposes, I'm going to apply it to all of the data. This is just for plotting purposes, not for statistical purposes. So I'm also in the main data frame going to create a PM 2.5 corrected column. And I'm going to also say apply it to all of the data in that data frame as well. So the important distinction here is, sorry, I messed something up. What did I do wrong? Oh yeah, this should be. The important distinction here is this column, this row that's highlighted right now is applying this correction, this linear regression model that we just developed to the testing data only. So if we were going to calculate the R squared, the mean absolute error, etc., we would want to do that against just this testing data. And I have a step that does that in the code. I think in the interest of time, I will leave that to your homework. But you can see in the code that we have we would want to do the statistics on just this testing data because that is more independent than the whole data set, which is down here at the bottom. But for plotting purposes, it looks kind of ugly to just show the testing data set. So for plotting purposes, we're going to show it on the whole. And then what I can do is then just make the plot. I am on my last couple of minutes here, so I'm going to have to paste in the plotting code. This plotting code comes from the matplotlib package in Python. So this is similar to the pandas, but a little bit different. I think maybe James or some others from Afri-SET have explained the differences and shown you the plotting code. But anyway, what this does is it plots the time versus the purple air concentration versus the embassy concentration, and then versus the corrected purple air concentration. So using that linear model. All right, so if you run that, you'll get what I am now showing on the screen. I changed the colors a bit. You can look at that in the code to be a little more intuitive. All right, so what we're seeing here is the purple air the PM 2.5 concentration versus month, and this is in Accra at the US Embassy. The purple is the purple air. The blue cyan is the embassy data. And then the sort of yellow-orange line is the corrected purple air data. So this is what we generated by using that linear regression approach. So if you just compare the purple to the blue, again, this is what we had seen earlier, you do see a lot of disagreement. I didn't show you the R squareds or the mean absolute error, but just because I've worked with this data so much, I know that the R squared is about 0.6. The mean absolute error is about 7 micrograms per meter cubed or something. It's a fairly biased and not highly correlated data set. When compared to this embassy data, which is sort of the ground truth. Now we apply this correction factor, we get this orange line. Now look at the orange line compared to the blue. It's much closer than the purple line. All right, so you can see it tracks fairly well. It's still not perfect. It's still some deviation, but I can tell you from you can see this in the full version of the code, and I can also tell you from memory that the R squared goes up to about 0.8, and the mean absolute error goes down to about 3 micrograms per meter cubed. So we've significantly improved the statistics. Again, that would be just on the test data set. All right, so I wouldn't apply all those statistics to the entire data set because that would be overlapping with some of the data that was used to train the model. So when I say that the R squared improves by that much and the MAE improves by that much, I'm talking about just on the testing data set. All right, so the last thing you can do is, if you want to know what the coefficients are, what are the parameters of that model that we just developed, that correction model, you can ask it to print out the coefficients. And it's going to print out several coefficients. Basically, maybe in the interest of time, the equation that it's basically doing is reference PM 2.5 is equal to 0.49 times the purple air PM 2.5 plus 0.45, plus 0.45 times the temperature minus 0.16 times the relative humidity. All right, so that is the model basically. So if you have purple air data, you have temperature, relative humidity, you multiply the purple air data by 0.49, multiply the temperature by 0.45, multiply the RH by 0.16, sum the first two things, subtract the last one, you will get the reference PM 2.5. So that's basically the model. That's what this yellow line, this orange yellow line is doing. The last thing I'll say, I know I'm out of time, is that, again, you could try this with other models. You don't have to use a linear regression. Linear regressions are nice and simple, and they also allow you to write an equation like this at the bottom. If this was a random forest, XGBoost, neural network, whatever you want, there's not like an equation necessarily. It's sort of just this sort of algorithm. But that's going to be it for me. I know lunch is probably ready. The data, the code in the data is all available to you, so you can try this on your own for homework if you want. I'm available for questions. I can sign in later today, or you can email me, or I can sign in tomorrow as well on the Zoom. I'll coordinate with Vic on that. But otherwise, hope this worked for you. Hope you got something out of it, and enjoy your lunch. And back over to Victoria.
Thank you so much, Dan. I think we can give it up for him. So if there's any question or comments, or you need any clarification, please, we can follow up in the WhatsApp group. And then also, you can equally send him an email as he suggested. And if we are fortunate enough to have him online, I think we can do that or have the discussion with him. And before we go for lunch, Sarath would want to take us through briefly his introduction before the main session begins. Just some few minutes, then we go for lunch.
So this afternoon and tomorrow morning, we will jump ship. This is not about monitoring and how do you do monitoring and how to deal with the monitoring data, what we saw in the last 2.5 days. This is about modeling. So the modeling comes in at the city level. So if you do the monitoring, you get the data. What do you do with it? Okay, it's not about just making those lines, right? You have to tell a story. What does that line mean? Okay, you bought a monitor, you set up all those monitors in the last 2 days, you put them in the city, okay? You're getting the data and you're drawing those lines. So somebody is going to ask you, how does it matter if the pollution is 100 micrograms per meter cube? Or it's 20 micrograms per meter cube? Why should I worry? Right? Okay, so this is where modeling comes in. Okay, somebody asks you, why is it 100 micrograms per meter cube? Okay, you You did all the work, you put a monitor, and it says average is 100 micrograms per meter cube. Where is that pollution coming from? Right? Say a public official like Ibrahim, where is he? Sorry. Okay. So no, he will ask, right? Okay, what do I do? What are the policy questions that I can answer? Okay. So in the afternoon, after lunch, and tomorrow morning, we will go through these different steps. Okay. If I have this information, how do I use to tell a policy story? Okay. So we will go through in step by step. You don't have to load any software or do anything. Everything will be in Excel. We will be giving you Excel tools. I think the link I sent yesterday, they had lots of those tools. So while we are talking, you can just download the files. They are really small files. Okay. But before we do that, I want to give you a glimpse of what we did in Kampala so that you have an idea of when we put all this information together, how does the story come about? Okay, this is the next step. Okay, how do we use information? That's the next step. Sorry, he's sitting right over there. Okay. So for Kampala, I mean, that's the big, there's a words that we keep using in the modeling world. One of the words is airshed. Airshed means when you draw a box for a city, that's your influential area. I mean, that's the area that you are interested in. It's not about just where you put the monitor, right? Eventually, decisions are not going to be made on where you put the monitor for the city. It's always about the city. Okay, airshed. How big is the airshed? So that's the Kampala's airshed. Okay, so what we did is we pulled a lot of information that's already available. No, something that Cosmos was talking about. For example, that Google Earth engine, right? It has lots of information. You have to work. It's not easy. But once you draw a box, you can pull a lot of information for that box. Okay, like where are the water bodies? Where are the roads? These roads can be broken down into different primary roads, secondary roads, all kinds of things. This is for modeling. Later on, we'll come to that. Okay, monitoring. This is the AirCo group. They do a lot of monitoring. So you can draw a lot of lines. You can draw all these variation plots. Okay, but it only tells me how much is the pollution. But I'm interested in why is there a pollution? Okay, I want to answer that question, right? So these are some of the fields you can pull from open resources. Google Earth Engine is one of the examples where you can pull all these things, but there are other resources as well. So we'll go through that as well. So as simple as this, urban built up area. How much has the urban area increased in my city? What is it a proxy for? One is in economic terms, development, but in pollution terms, there's a lot of construction. Okay, there's a lot of demand for transport. There's a lot of demand for commercial activities. There's a lot of demand for electricity. Okay, so obviously there is also a lot of industrial growth. All that is contributing to the pollution. So we can, just looking at this, how much of the urban growth has happened in the city, we can pull a lot of that stories. Okay. Same thing with the land use and land cover. There's a lot of resources for population data. How much population has increased in different zones. It's not about just where I'm interested in, but the entire airshed. So we pull a lot of this information that's available also in the global models and try to understand the local layout. Okay. So Google Earth, just the images of Google Earth can also be an excellent resource. Again, it's an open resource. Don't think in terms of AI and ML. This is about manual labor. Okay, you really have to look at the map. Okay, figure out what's happening in my map. Okay, in this example, the 4 things what I'm showing you here, these are quarries. They're all over the airshed. Okay, what happens at the quarries? The breaking rock, a lot of dust is flying. All that rock is being moved to the cities for construction. Okay, There's a lot of dust that keeps coming up. These are not official sources. These are unofficial sources. They contribute to the pollution. Okay. If we just say that, oh, I'm measuring 100 micrograms per meter cube, it could be coming from exhaust, which means that we are overestimating one problem and underestimating what is actually happening in the airshed. These are the things we can catch using an open database. Okay. Google Earth can be used for that. Okay. Even we know if there is a cement plant. Okay. There's a 100 million ton, 100-ton cement plant that is there in the city right outside. But how big is it? Okay. If you go and ask them, they will ask you 100 questions. Why do you want to know? But you don't need to do that. Google Earth will show you exactly where it is, how big it is, and general, a quick search on the cement plant will give you all the information that you need to know. Like how much coal is being used there, how much clinker is being processed at the plant to make the plant. If they're making 100 tons of cement, any engineer can quickly do a back calculation and tell you how much clinker is required and how much coal is required. Okay. If they're not doing any controls, we can calculate how much pollution is that plant being generating. Okay. That's the modeling. Okay. It's not about just, I need to have a measurement at the plant. No. We just need to know the plant exists, how big it is, and we can do all the back-end calculations. Okay. Same thing with the landfill. It's hard to have a paper saying how big is the landfill. But now we have so many images. Over the year, how the landfill has changed. Now we can collect all this information directly. Okay. This is a Kiwangi thermal power plant, about 50 megawatts. Okay. And you can collect a lot of information on the road transport as well. So a lot of these documents exist, but we have to massage them. Okay. Nobody is going to give us a nice little table saying, oh, we have so many cars, so many vehicles, so many imported, so many locally made. Not possible. You have to keep talking, collect a few reports and put this together. So what we have done is a lot of this, and eventually you can make a emission map. Okay. All modeled. We're not saying that this is measured. This is not measured. This is modeled. Okay. It helps us how? It helps us to create a ground reality. Okay. And you don't have to blindly follow it. You don't have to blindly believe it. So this is where validation comes in. We have to validate what we are modeling with what we are measuring. Measuring. This is where all the work, all the talk that happened in the last 2.5 days, that comes into picture. Okay. We need that ground representation from monitors as well. Okay. If monitors and the models can talk to each other, which means that we can use this information to build scenarios. Very important. A big question that was asked to Gift as well, I think you asked, about outside contribution, transboundary contribution. In the measurements, you can't tell how much is local and how much is not local. But if we do an emission inventory, if we take a meteorology, combine that in a chemical transport model, we can tell how much is coming from outside. So for example, in the Kampala's airshed, especially in January, February, and March, outside contribution is very high. Okay. And no, the measurements being taken, we have the nice graph, which basically says, look, Jan, February, March is very high. But why only in Jan and Feb it's high? Okay. So here we are seeing a lot of contribution is coming from outside. So what is outside? So in the model, we can actually break down what is coming from outside. So especially in January and Feb, a lot of fires happen in northern Uganda. So a lot of that actually, the secondary pollution actually comes down. The POA is basically organic aerosols, secondary organic aerosols. So if you have fires, biomass is burning, you have a lot of organic aerosols. And from north to south, the movement is about 600 kilometers. That's enough time for a lot of secondary aerosols to form, and that shows up in the monitors in Kampala at the boundary. Okay, you can't tell this from just monitoring. Okay, you want to tell a story, you have to do some modeling as well. So what we are going to do is, what is modeling? A lot of the time you have fear. We want to remove that fear. It is a lot of work, but if you do it systematically, if you go step by step, exactly the way Teddy was showing you, step by step, how do you assemble a monitor? Same thing. Assembling a model is also exactly that. Okay, so what we're going to do after lunch, we'll start with one of the puzzles, okay, and we'll go step by step. Okay, so I shared the link already. So at least for the first session, if you can, after you come back, you can download these air quality scenario players. We will be playing with those. Okay, cool. Now we go for lunch.
So for our next session, we'll be having Professor Sarath Guttikunda taking us through urban emissions. Now, for his topic, he will be handling bringing together data and scenario players, a demonstration of SIM Air Toolbox, and other calculators, which will be followed by hands-on time and then discussions. Now, Professor Sarath is the founder or director of Urban Emissions. He's the founder, director of Urban Emissions, and you can find his information on urbanemissions.info. He's coming from India, so please let's welcome him. Thank you so much for being here.
Okay, so we will come to these presentations and all again. But before that, I also have some handouts. So while we are talking, I also want you to keep going through this. Okay. So first thing, when we talk about air pollution, most of the discussion that we saw so far is only about PM 2.5. Okay, because that's what we mostly measure. All the sensors that you saw is also about PM 2.5 only. But generally speaking, if you want a little bit more background on what are the other air pollutants which are important to us, okay? Especially when we're talking about policy. Policy can't be done only on one pollutant, right? Different places have different problems, so we want to understand that. Again, these are all in a comic book style, very easy to understand. So afterwards, Ibrahim or somebody will pass around all these things, but you can also come and take it. We also have a primer. This is on air quality monitoring. Okay? Because generally, I understand that you have a good grasp on how to assemble a monitor, right? I've seen it. Now, I give you 10 parts, you put it together, and then you're making it working, the data is going online, it's all happening. So you're really good at that. But if somebody asks you, what are the thumb rules of air quality monitoring? Okay? Where should you monitor? How should you monitor? Or if you have the monitoring data, what are the 3 things or 4 things that you want to do or can do? So it's a small primer. Okay? So you don't have to read a big textbook. You can read a small textbook. Okay? Now, earlier, the presentation as I was showing you, it has so many components, right? So air quality is not about just monitoring. It's not about just putting a monitor, getting a data, drawing a graph, and then saying this is high, this is low. No. There are many, many dimensions to air quality monitoring. Okay? Now I'm sure if you have in your classes, whether you're taking them or you have taken them, you learned a lot about what is air quality, where it comes from, and all those things. But the next step, what you're trying to do is build an information base that will eventually be used for policy discussions. Okay? So there is a certain language that goes with that step. Okay? So we have what we call as ABCs of air quality. Like very simple. In C, in letter C, you will see co-benefits. Okay? What does co-benefits mean? In the air quality world, in the air quality community, when you go to a conference, like earlier in Gift's presentation as well, he used that word, co-benefits. What does it mean? Sorry?
It's like two parties benefiting. Yes, so there are some interventions for climate change, there can be a benefit, but for health too, we benefit. So co-benefits for climate and health.
So combined benefits. So here the parties are climate change people and the air quality people. Okay? So there is a certain language that goes with that whole concept. Right? So what is co-benefits? So things like that. So this is what we call as ABCs. If in general, if you are a person that has no background in air quality, but if you want to act like you know everything about air quality, this is the only thing you have to read. Okay? So it will give you all those concepts. Okay? So take a look at this. Okay? So we have something called source apportionment. This also came up in Gift's presentation. Somebody asked an interesting question on the sources. Okay? Again, this is a phrase that is used a lot in the air quality world. Okay? Why do you need to do source apportionment? Why do we need to do source apportionment? Okay? This source apportionment means trying to understand where is my pollution coming from. Okay? This is a step after you do monitoring. Okay? So when you do monitoring, the information that you get is how much is the pollution. The next step is where is that pollution coming from? Source apportionment. You are trying to apportion what you are measuring. I am measuring 100 micrograms per meter cube. So I want to know where is that 100 micrograms per meter cube coming from. That is source apportionment. There are two different ways of doing source apportionment. This is a very important thing, especially for policy purposes. Okay? If you are in the monitoring world, this is something that you should definitely learn about, because that will be the next step. So again, in a very comic book style, trying to understand the technical phrases and the jargon of source apportionment. So I'll leave these here. So please take a look. Okay? Now, one more step further. So this is for if you really want to get into actually doing some modeling, emissions and pollution modeling. I hope that at the end of this one day, you will get a little enthusiastic and you actually want to do it. But you can take a copy of this as well. I mean, we try to, it's like a textbook, but we try to use as simple language as possible so that even with limited technical understanding, you'll be able to follow the concepts. Okay? So we will go through some of these things while we are playing with the tools. Yeah? The very first chapter in this talks about why or how monitoring and modeling comes together. The presentation I showed you, what we have done in Kampala, trying to build a story using the monitoring data and the modeling data, top down and bottom up. Okay. The first chapter, it's only 3 pages, it will explain to you why we have to do both. Like, we shouldn't be happy with just doing monitoring. Okay, we have to take the other step. Okay, so what are the benefits of doing that? So, Ibrahim and Matthias, maybe you can just distribute them as we are talking. Okay, so every once in a while I'll be referring to some section in there, okay, some chapter in there, so you can take a look. At some point we'll also have a small quiz. So remember what I'm talking, so because you're going to have a quiz. Okay? So remember it. Okay, we'll skip that. Okay, I have a lot of presentations as well, but I don't like to show all those presentations. Those presentations, these books, they're all for reference. Okay? They're all for reference. Now, the very first thing that I told you, why do we do modeling work? Or why do you do monitoring? Forget modeling. Why do you do monitoring? To know the concentrations of pollutants. Okay? Not just in one place, but across the city. Okay? Now, you are presenting your work to a policymaker. Okay? So that policymaker, like in your EPA, for example, they're not interested in just one location data, right? So I want to know what's happening in my city. So they have a boundary, city has districts, okay? So I just found out that Accra region has 15 districts. So if a decision has to be made on what to do in Accra, the decision applies to all 15 districts, right? It's not only for one district. You have to do for all districts. Okay? You're monitoring in all those districts. So you have some information for each of those districts. Okay? So here is an example with 10 zones. So now you are trying to present what you have monitored, you have gathered, data that you have analyzed to a policymaker in trying to come up with a scenario. Okay? Eventually, that's what going to move the needle, right? They're not going to just say that, okay, you have measured 100 micrograms per meter cube, then I'll put the number there. No. So what do we do about that 100 micrograms per meter cube? How will that change our overall numbers, like health numbers, okay, compliance numbers, exposure numbers, all these things? Because that's the next step, right? It's not about just getting that data. How do we use that data? One example, if your city is 10 zones, okay, you've done the monitoring or you've done the modeling and you have an average pollution value for each of those zones, each of those districts. So you have those 10 districts, 10 concentrations as an average for that district. And you also have how much population is living in each of those districts. Okay? The concept of sum product, do you know, in Excel or even in general mathematics? Sum product. So the idea is we have to calculate this population weighted concentration. Where do we use populated weighted concentration? In health impact analysis. Okay, so if you want to do health impact analysis, you want to know how many people are dying for being people exposed to that kind of pollution. You have to calculate what we call as a population weighted concentration. At the end, all the policy decisions are based on that. It's a very simple thing. You multiply both the columns and you divide it by total population. It gives you population weighted concentration. Okay? if a zone has more population and more concentrations, obviously more weightage is given to that zone because there are more people are being exposed to more pollution for much longer time. That's what it means, population weighted concentration. Okay? Now, how do we use this for building some scenarios? Okay, so you're sitting in front of a policymaker. It's a very simple way of presenting your work, saying, okay, if I can reduce 20%, 30% of pollution in zone 4, how will it change my city average? Because at the end of the day, for the policymaker, that's what interests him, right? Or him or her, isn't it? Ibrahim, I was actually looking for you earlier, but I thought it was. No, when you are the only official here, that's that I can point to. So you are interested in how can I reduce 10% of my pollution in my city? Is that not a question? Yes. So where do I reduce that? Which zone? Do I do directly all the work in central Lagos, or maybe another district in Lagos which has higher pollution but lesser population? I can do it cheaper, work there. Maybe that will reduce the concentrations. That's you have to optimize. Correct, right? So which zone should I concentrate on? Because I don't know all the zones, but you will know these districts, right? So you will say that district 2 is a lot more polluted, but maybe we can work there. But you can also say that maybe winds are blowing more from the district 3. Maybe we should concentrate there because that's contributing more to the city. Because you understand the map. Okay, data is coming from the monitoring stations, and then you have a list saying each of the districts are polluting so much, so much, so much. Okay, how much can I reduce in each of these districts so that my city average is down by some percentage? If your goal is 20%, overall goal is 20%. So at that bottom, the net reduction, let me increase this a little bit. Okay, so this net reduction, the overall city average has gone down only 4%. Okay, by reducing 30% pollution in zone 4. Okay? And you can do a little bit more in all of those zones. So what this does is it gives you an opportunity to talk to all the people in the districts in a very, very simple way without complicating the science. Because they don't have to sit down and do the monitoring. You are doing the monitoring, you bring the data. Now we'll build stories. Some official from zone 3 will come and say that, no, I can't do anything. Possible, right? So zone 2, zone 3 says, okay, 0, fine. Can we still achieve the goal? If we don't do anything in district 3 or district 4, can we still achieve the goal of 20% reduction, overall 20% reduction, overall 30% reduction? How much do we have to do the reductions in each of these districts to reach the goal? Okay, in a very simple way. Okay. So here the idea is not a model, idea here is a concept. So we are trying to show how much work we have to do district wise to achieve a goal. Understand? Yeah. Yeah.
In the population, you have where within the population you have vulnerable subpopulations.
Yeah.
Okay. So within the general population, we have subpopulations children, women who are a bit more vulnerable than the general population? Is it able to take into account those differences in the... I hope you understand my question.
So those are what we call as nitty-gritties,
We call...
minor details, all those details. So here, nitty-gritties means like picking small details. Okay. Yes. Technically speaking, yes. Now you have to think in terms of a person sitting there making decisions. They only want to know how much work they have to do. The goal is, okay, somebody from the top has said city of Accra has to reduce their pollution by 30%. That's the goal. Now, your job is to tell that person, okay, how much do we have to do in each of the districts to get that goal? Okay. So what you're asking is also there in a different version. Things get complicated. Now, what you're asking, can we break up the population? Of course, we can break up the population by age, by gender, by occupation, all those things. Next level. You will see another Excel sheet which has a lot more complications. But you have to, important thing is you need to get interest of the person who's going to make the decisions. If from the beginning, if I show you an Excel file or a program or a model which tells you you have to fill 1,000 things, what will happen? To get to a decision, you have to fill 1,000 things. What do you think will happen? From the beginning, you will be discouraged. From the beginning, you will be disappointed because you can't fill all 1,000 of them. So the idea is to raise that interest. So your question tells me that you're interested in this, because now you want to add details. That's a good thing. Then, which means that now you have to go and get those details, fill it. Okay. So the idea is to have that discussion. Understand? So later on, you take the file and then you figure out for your city, these are the values that I always get from my monitoring stations. Or in your district, in your city, you may have only 4 districts. Fine, use only 4. Okay. Put your average numbers that you have from your monitoring network, get the population data, okay, and see. It's a simple Excel file. It's not going to crash on you. Crashes, open it again. Okay. Nothing to load. You'll have it on your laptop all the time. Okay. But playing will give you 10 different scenarios. So which means that you can talk to 10 different officials. Okay. Now, we will slowly complicate. Okay. This is exactly the same thing. Exactly the same. But we are not talking about districts. We are talking about sources. Okay. If you have that kind of, right now you're only doing monitoring. So you only know how much is the pollution. But if you go to the next step and you tell me, I don't know, I don't even know, not only I know how much is the pollution, but I also know where is the pollution coming from. Okay. I know how much transport is contributing. I know how much is industry is contributing, how much is coming from local, how much is coming from not local. Okay. Again, same policy discussion will happen. Okay. I have 50 monitors in the city, and my average for city is here as an example, 85 micrograms per meter cube. Okay. And these are my sources contributing to the problem. And these are the percentages. You can start building scenarios. You can go to the transport department and say that, okay, how much can you do? My end goal is to reduce 30% of the pollution in the city overall. You understand? Now, transport is contributing 10%. How much can you do? Okay, I mean, this is just a random example. I put 10, 10, 10, 10, 10, but you can change it. So you can say that, no, transport is not 10%, transport is 40%. You can play with that. The Excel file is with you. So I want you to make a case for yourself. In your city, put your numbers. It's an Excel file. You can build 10 scenarios, 20 scenarios, 100 scenarios. Okay. How much do we have to do in each of these sectors to reach that 30% goal? Ultimately, that's what's going to move the needle, right? So we don't want to just feed people with monitoring data. We also want to be part of that story, right? Again, simple, one step at a time. So you can drive the conversation from how much is the pollution, whatever you're already doing for the entire city. Take it to the next step. Where is the pollution coming from? If you have that information also, you can do this. Okay. So you take those version 1, version 2. Version 1 is how much? Version 2 is where is the pollution coming from? You put your own numbers and see what happens. Okay. Now, logically speaking, yeah.
If I get you right, which means that let's use this as an example. The institution has to tell you how much they want to reduce the pollution coming from that source. Assuming they don't know, maybe you're talking to a policymaker and so how much do you want us to reduce? And they're like, oh, we just want to see a reduction. What is the ideal percentage you should be working at?
Doesn't have to be 30%. You can come up with your own target. Okay. What is the global target that we can think of?
I would have said 50, at least try and solve the issue by half.
For example, WHO guidelines. That's a global benchmark.
Yeah,
right?
okay.
WHO guideline. I want every city in the world to meet WHO guideline. The WHO guideline is 5. Okay, going from 85 to 5, it's going to take a lot of work. Okay, so but it's nobody is going to stop you. It's a scenario. You can make a scenario saying, if we have to go to 5 micrograms per meter cube, how much do we have to do? It's a scenario. Whether we'll achieve it or not, doesn't matter. It's a heroic benchmark. We want to be there. But you can also do it instead. Like 20%, we have to do this much. Now, in the cost benefit analysis, there's a word for it: low hanging fruit. Okay, what is the cheapest and the easiest thing you can do in the city to get those reductions? Higher, 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 more and more you want to do, obviously it will get more complicated and more expensive. Okay. Suddenly we can't just wake up and say, my entire city, I want to be solar. Of course, it will be super nice, but it's also a super expensive thing. It will have excellent benefits, but it's going to be a super expensive thing. But if we said the lowest hanging, we will at least start taking care of our waste. We will make sure that no open waste burning happens in the city. It's the lowest thing that one can do in a city. Maybe it will reduce 5%. Fine. I mean, any percent reduction is good. Okay. So how much can we do in each of these sectors? It's a start for discussion. Okay. Somebody says 10%, 5%, or 5 micrograms per meter cube. Ultimate goal. Why not? So what's the Ghana standard annual? Is there a standard? How much?
I think it's It's similar to the WHO. I have to cross check for you. 35.
35. Okay. So India's annual standard is 40. So generally, when we make scenarios, we make for 40, saying the entire country should be at least under 40. That's the goal. So your like national goal is 35. Like ultimate goal is 5. In anywhere in between, no scenarios. Okay. So now we have a way of dealing with this. With how much is the pollution? Can tell a story based on just measuring what's around the city, right? If we know where is the pollution coming from, you can also build scenarios. Okay. What's logically, how do we complicate this? How do we complicate this now? You can complicate it. This is where that 1,000 things comes in. No, more information you have, you want to do more. Okay, how do we complicate the next step? So we know where and we know how much. So what if every district, sorry, that's the, yeah. Okay, so this is version 3, same as version 1, but we're using a new feature in the Excel file. It's called a solver. It's called a solver. Okay, so you just have to activate it under data. You will see it. Okay. So the idea is again to exactly to your question, how much do we have to do? Okay. If the city says that, okay, I have no idea. I only know how much is the pollution and I know how much is what's the target. Okay. But you bring those 10 people from the 10 districts, you put them next to each other and say, okay, how much can you do in your district? Okay, district 1 says, okay, I can do maximum 20% or 10%. The district 2 says, okay, 20%. These people will say 40, 40, 40. Okay, 20, 20, around 30, like this. Maximum, how much can you do in each of your districts? If they have limits could be because of budgets or people or whatever. You have limits, okay? So you have those limits, you have concentrations for each of those districts, and you have a target. My target is I want to reduce 20%. I want net reduction of 20% in my city. Okay. Then how much do I have to do in each of those districts given those constraints? Those are my constraints. I can't do more than that. Okay. So what is possible? So in Excel, you have something called a solver. So you can click on that. Sorry, what happened? Sorry, I was supposed to activate the solver. But Sorry, this is my new laptop that I got. And then okay. So under data, you will see this solver. So you can use this function and say that, okay, I have these constraints and this is my target and these are my concentrations. So how much do I have to do? So if you say solve, it basically does some work and it basically says, okay, you have to do so much in each of these places. You will reach your target of 20%. So if you click on the solver, so here you can add all the constraints. So if you see, you see that I can, the amount of reductions is in the F line, F column. These are the columns. This is the amount of reductions that I want to achieve. And these are my constraints in the I column. So this is the I column that you have. This is, sorry, J column. So these are the constraints. And I want a net reduction of 20%. 20% is 0.2. So if you say, okay, I don't want 20%, I want 30%. So we'll do that, value of 30%. So I want net reduction of 30%. And you press solve. And we says, okay, you will get a 30%, but you have to do so much in each of these places. Okay. So at some point, you can also put in 50% and it will tell you that a solution is not possible. Why? Because none of the districts can do more than 30 or 40% in general. So reaching 50% will be really, really tough, not possible. So you can also use this to show the constraints. Understanding? You have to at least nod so that so I'm using the simplest of the simplest concepts. Okay.
And then you ask them how much they can reduce their pollution or emission. After they've given you how much they can, with you as a data analyst or whoever, you use the solver and then you put everything together. So the solver puts everything together and gives you the total amount you can reduce when looking, you have to reduce looking at their okay, thank you.
So this is same as the first file that I showed you. Just we added an extra function that is already there in Excel, the solver function. So if you don't want to decide how much each of those districts should do, you want to have a mathematical solution, you can use the solver function. That's the idea. Okay? Yeah.
I think maybe if
No,
for-
she didn't ask questions, she summarized what I said.
Oh, okay.
Yeah. So she wanted to understand, did I understand it right?
Okay, so mine is, for instance, all the work you are doing it in the context of a research work. So let's say you are not involving any policy people or anybody for now.
Yeah.
You are doing a research work.
Yeah.
And you want to, at the end of the day, show what should be done to bring the, so in that case, the averages you were using, how do you arrive at those ones? Do you get my question?
Yeah. So the average, as in the concentration averages?
Yes, where you gave the different districts different. How do you do it if you are doing it as a researcher, not involving any policymakers or that sort of?
So you can get those averages in two different ways. One, you tie up with a monitoring person, and then they are doing all the monitoring work. They're doing all the averages, and then they give you that value, saying district work concentration is 2, district 2 is this, district 3 is that. Second way, if you don't have anybody who can go and if you can go and ask, second way is literature. So you look at 10 different publications and say, okay, what are they reporting? Okay, so use that as your first case, saying this is what is published in the literature, saying each of these zones are polluting so much. Okay. Okay, I'll remove the sleeper function. So you can get that. If you don't want to do that either, a third option also exists, what we call as global reanalysis files. The global files, which basically they're global programs which combine a lot of the inventories, meteorological data, satellite data, everything, they nudge everything and they give you averages. You can use those as well. Okay. But very importantly, you can build a story just sitting at your desk if you want. You can build a story. Okay. Right here, when you have so many people doing monitoring already, they will know from your pockets will come out numbers like that. They'll help you fill those district averages. Right? But important thing is you understand. Okay. Understand? Yeah. So the idea is not just to do monitoring. The idea is how do I use this monitoring data to make people interested in my data? Okay. Understand? Okay. So during the break time, don't just run away, but maybe you can make a scenario and show me saying, okay, for my place, these are the numbers that I am monitoring already. This is my story. Yeah. Now, this oh, is this frozen? Okay. So this is version 4. What's happening is looks very confusing. Okay. But it is doing exactly what we did in version 1 and version 2. But now we have information on source apportionment. Where is the pollution coming from for every district? Okay. So now what happens? You have 10 districts, you have 10 sources. So your variables have become 100. So now we have to deal with 100 variables. Okay. Not a big deal. So you're doing that work already. Okay. You're already doing that work. Just looking at all of it together makes it very, it looks very daunting. Yeah. But no, you should not have that fear. Still the same solver, still the same button, press it. Okay. So here you can do the same thing. So now the question is not about how much you have to do in each district. If you have the information on source apportionment for each of the districts, but within the district, how much you have to do in various sectors. So for example, Central Accra, logically speaking, what could be the biggest source in Central Accra? Huh? Vehicle emissions. So logically speaking, if we concentrated most of our work in trying to reduce vehicle exhaust emissions in central Accra, you will have a bigger benefit. But you don't have to do, the idea is not to do all 10 in all 10 places. Okay, if we have to do concentrated work in some sectors, in some districts, what is that? How much is that? So it's very easy to put that together. So you can use this example and expand it. So you can say that, okay, in my area, I'm only talking to 4 districts. Fine. You can just zero out all the other districts, use only 4. Keep it simple. Okay. Keep it simple. Start with that. Then slowly, slowly you expand. Okay. Same functions, same distributions, same solver. Okay. So here, what you will see, the same solver, but now the constraints have actually increased. Not only looking at sources, but also how much areas, but also sources. And you can come up with a solution. Okay. How much we can do in each of those. You can create constraints on each of these. Okay. So afterwards, like if you want to form some groups, play with it, ask me questions. We can walk around and we can do it. But things always start on the first step. Use the version 1 and version 2, understand it. And then when you come here, this won't look so daunting. It will be like really quick. Okay. But the concept is important. You understand in the concept, like why are we doing this? Yeah. If I want an answer in simple language, why are we doing this? Why are we doing this?
Pollution we can reduce in a particular environment or a particular zone.
That's it. So we don't want to tell people only how much is the pollution. We also want to tell them what we have to do, because we can't do anything. I'm just a number cruncher at the time, right? I can't buy buses. I can't manage waste, but I can tell, right? That's the whole idea. But we have to tell in a language that everybody understands. Okay. I think this is all the discussion that Cosmos was talking about yesterday, language. Language is very important. Simple language. We want simple language, right? We don't want complicated language. You can't go to somebody's office with a monitor saying, look, I have 10 monitors. What do you think they will say? Like, what do I do with that? No, you know what to do with the monitors. They know what to do with the numbers. So you build a story with those numbers that they will understand, that they can play with. So this Excel file, you put it together, give it to them. Give them the Excel file. No, they'll open it. There's no loading, nothing, because it's Excel file, there's no fear. They'll open it for sure. If I give them a Python program, what happens? Nobody will open it. Okay? Because they're immediately, oh my God, like this sounds very, it's going to eat me. This Python is going to eat me. That's the first thought that will happen. No. But simple language, same message, simple language. Okay? Sorry, I'll remove the sleep thing. Yeah. Understanding? Okay. So more and more, the more you do it, we can definitely complicate this. Okay. Complicate a lot. Okay. That complication comes in this. Eventually, if you want to do a PhD or something, we can help you with that. Okay. In the when we're doing PhD, man, this is too small. You want to go much more than that. So the Kampala presentation that I showed you earlier, that has a lot of details. Now, spatial disaggregation, temporal disaggregation, gridding, all that stuff will come. Okay. But from the beginning, if you start there, it's not going to happen. You go step by step. Yeah. Okay. I'm not hearing anything from this side. So I really don't know whether understanding, not understanding, understanding. Hmm? Yeah. Okay, cool. How do we add? If you just press solve, it will solve for now. Yeah, it will. Has it found a solution? Yeah. Say okay. Yeah, so that's the solution you have already. Okay. Now change the constraint. You go back again, go to the solver. Okay. You say that, okay, so that's why you said 40% already. So it said if you want the 40%, you have to do obviously everything. But even after you do everything, you only reach 20% because of the constraints. Cancel that. Because of this constraint, these cities can't do more than that. So if you increase all that, you can increase the constraints, saying, okay, I mean, they can do a lot more. Now, if you do the solver again, okay, it should change. Hmm? Hmm. Open that again, solver. Hmm. Yeah. Oh no. So okay, you change this objective. That should have been this one. Yeah. That you can't change. Okay, don't change that. Because that's what you want to. You want the net reduction, that one. Okay, now press solve. Go back again. Okay. So value on. Okay. I don't know why it's doing that. Okay. Is doing the same thing over there? No, right? Mm, is this an older version by any chance? No, no, no. Population weighted concentration, it's calculating, right? Download it again and do it? Yeah. Don't change any of the equations. Okay. Yeah. So your target, you should only change the target, not the equations. Yeah. Yeah, just download it again and do the same thing and see what happens. Yeah. 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 So don't change any equations behind these. Okay. So all of these have equations. Don't change the equations. If you change the equations, then the solver won't work. Okay. But try. But generally speaking, you understand the concept. Okay. Okay. So this is the almost the final complicated version. Okay. So here we are looking at concentrations by grid, grid by grid, grid by grid emissions, grid by grid concentrations, and you have cost functions. How much does it cost to do something in each of those districts, each of those sectors? Okay. So, and health impacts. You can all bring it together. So the technical word that we use is integrated air quality monitoring. You're integrating everything. Okay. And coming up with the trying a solution for it, a solution that will work. Okay. Okay. Now, if you're still doing the previous versions, I'll wait. Yeah. Sorry. I will. Sorry. Hmm? So this is the main one. This is the SIMAIR. Okay. SIMAIR is simple interactive models of better quality. So there used to be very old times called SimCity. There used to be a video game where you build different things in your city and it will increase your carbon footprint and energy footprint. And then at some point, the city can't manage anything. Then it will die. The program dies. It used to be a game. Okay. So like that. So we call it SimAir, simple interactive models for better air quality. So this is the ultimate. Okay. So you want to bring in everything that you know from every different place, not only your monitoring, your meteorological data, cost benefit analysis, health impacts, everything is coming together. But I don't want to get daunted for it, but the presentation I showed you comes from something like this. So we customize this for different cities and we go there and show. But important thing is you should start with the basics. First step, slowly complicate. Every version 1, 2, 3, 4, 5, 6, and this is the last one. Every version complicates the calculations and asks you for more and more data. Okay. But at the end, we want to have a story on how much is the pollution coming, how much is the pollution, where is it coming from, okay? What are the sources contributing, and how much do we have to do in each of these places to reach a target, okay? So that target could be compliance. So when we say compliance, I want my city's average to be certain number. I want 35 micrograms per meter cube. That's a target. Or WHO guideline, or a percentage. Okay. Or health impacts. It can also be health impacts. I want to reduce exposure rates by 10%, because that will be very different. That's where your point comes in, because the exposure rates for children will be different, vulnerable population will be different, adults will be different. So you'll have a different set of solution that comes out. It's possible, but the concept remains the same. Okay. Are we on the same page? Yeah. Key is you have to start doing it. Okay. Otherwise, nothing. I mean, I'll show these things and I'll go away. No, Cosmos showed things, Teddy showed things, Dan showed things, all of us showed things. But if you don't sit down and practice, it's of no use. Okay, you have to practice. So that's why we want to show you simpler things, easier things. So start with these. And slowly, we can help you complicate things. Complicating is super easy. Okay, starting is very, very hard. We want you to start without any fear. Okay. Okay. So somebody's asking for where to find the solver. So in the Excel file, if you go under options, okay, you will see add-ins. Under add-ins, you basically this Excel add-ins. If you click on go, then you will see these options. Just click on solver, just make it highlight that and say okay. So when you do that, under data, you will see it, solver. Okay. So a quick question. I was not going to give you Excel lessons. So there are actually a lot of videos online on how to use each of these functions. They'll actually give you a lot more explanation. Okay. So the idea of a solver is if I have certain constraints, so you can, okay, this program doesn't have anything. So let's go there. Yeah. Okay. Constraints means how much one can do per certain variable. Okay. So you can enter all those constraints in this constraint box. So if you want to add a new constraint, you can say that, okay, I'm going to add a new constraint. I want this concentration to be less than or equal to, no, you can say, okay, 30. Okay. Add. Okay. Okay. So now you will see that a new constraint is added into this. So this C10 going under 30, this was not there before. Now a new constraint has been added. Okay. I'm just showing this as an example. Don't do this in the same Excel file, but do it in a separate Excel file. Okay. This is just a random thing. I'm going to cancel it. So that's how you add constraints. Then you basically objective. You have to set an objective. So what is our objective? At least in this file, our objective is the % reduction. Okay, how much do we want to reduce? So I said D20. So this D20, this cell, I want to be 30%, means 0.3. Okay, I want it to reach 30%. That's my objective. These are my constraints. So solve it. Okay, this will crash because I put in a very random constraint. Okay. Okay, so that's how you keep adding. Okay, so if you want to add more constraints, you can add more constraints. Okay, but you also have to look at the variables. In this sheet, we are only working with 10 variables. So we have 10 constraints. For each of those variables, you have a constraint. District 1, one constraint. District 2, one constraint. District 3, one constraint. In this big file, in this version 4, you will have 100 constraints for each district, and for each source you can have a constraint. Okay, so you have 10 multiplied by 10, you have 100 constraints. The process is the same. You go to the solver and you can add constraints. So here we added a constraint as blocks. Okay, I want this entire block to match a certain block. Okay, you can do cell by cell or block by block. So, and there are a lot of videos on how to use Excel. So you can press on YouTube videos on how to use solver. You will have those lessons. Yeah. Okay. I'm assuming you guys are doing something with those Excel files. Yeah. Yeah.
Okay, thank you. So far, the example we are working with is for the whole city. Okay, the macro environment. So if, for instance, you are interested in the micro environment, for instance, schools or households, can this work too? Okay, so they don't work for the micro environment. Oh no, but you know the microenvironment too, we have situations where we have a lot of outdoor emissions coming inside. Yes, so for the outdoor ambient space. Okay, thank you.
Only and looking at from a city's perspective. The idea is that I want something in my city done. It's not about I want something done on my street. So street models are very different, complicated units. This won't work. So this is the idea to figure out what needs to be done. And then the next step is whether that will get done or not. That's a completely different ballgame. No, the policy discussions and negotiations and all that stuff. That's different. But at least we should be in a position to tell what needs to be done in the city because of what we are seeing in our monitoring network. How do we do that? This is where it comes in. Okay. Yeah, not for micro environments. Different.
Question. Looking at the model for the average. Looking at the equation for the new average, when you click on it, it gives you 1 minus the average concentration.
One is reduction. If you say 10%,
Yeah, so I want to find out why the 1.
1 is 100. 1 means 100.
Okay.
100 minus 10%.
Okay.
So 100% as a number is 1.01.
Okay.
So even if I put 100%, it will change into 1 automatically. Yeah. So these are what we call as scenario players. The idea is to generate scenarios based on the kind of data that you have. Whether the data is coming from monitoring data or modeling data or some satellite fields, reanalysis fields from different field groups. So you can use any of those and start putting it together. Okay. Yes.
Please, I have another question. So can this be done for a number of years in terms of the cities and then the source apportionment? Can you do it for a number of years? It can be done.
Yeah.
Okay.
So we have another version which has multiple years also. So, but then again, if you understand these steps, it's just adding a complaint, another constraint, right? So it's just instead of doing 1 year, we'll do 10 years. Means 100 variables multiplied by 10,000 variables. Okay, that's where things get more and more, but definitely possible. Okay. You ready for a quiz? Let's do a quiz quickly. So even I have an idea of how much you understand, what kind of background do you already have in this field, because the next step, as we go more and more, there will be more concepts that we will talk about. Okay. Don't be afraid. I'm not going to judge you. You don't have to give me what you're doing, nothing. Um, okay, for this, I will need either your phones or your laptops. You used Slido before? Slido, yeah. So basically, yeah, the quiz is on that. So there will be a QR code that will come. You just log in and you press A, B, C, D. Okay. Okay. Can we do this? If you either go to your phone or on your computer, if you go to slido.com, you'll say, you can see join the quiz. You don't have to write your real name. You can just say ABCD also, that's fine. Okay. When you join, it will show how many people are joined. So I still have 0 there. Okay, I have 1, 2, 3. Is that you, Maple? Okay. Okay, only 4 people interested in taking the quiz. Okay. So what do we do? Shall we just go with the 8 people? Huh? Yeah, 15 people. Oh, okay, because for me, I can't see for some reason. Okay. Okay, let's just go ahead. Okay. What do you think is the answer? Either my internet is slow or I can't see any answers. Anybody pressed answers yet?
Yes.
Okay. Okay, so there's no, I think my internet is down. Yeah. Okay, I think I'm going to go ahead because my internet is seems to be down as well. So verbally speaking, what's the answer? C? Anybody else? C, excellent. C is the answer. Okay, the people are showing up. Okay, That's excellent. Because the last time I did this test, the answer came 60%. No, only 60% of the people said. So the general confusion is between radius and diameter. Okay. But the answer is it is diameter. Excellent. Yeah. Okay. Quickly. If you, this is completely very simple 101 exam. No, not even exam, quiz. Okay, we have 22 people. At least if 10 people answer, then I'll move forward. Okay, I think I'll move forward. Wow, excellent. This is, we heard one answer as C, but sulfur dioxide is the right answer. Okay. Which of the following is not a necessary ingredient to produce ozone? Of these four, we don't need one of them to make ozone. If you want to use ChatGPT, that's also fine. I'm not judging. No, at least you know where to find the answer. So good. Okay. So the answer is actually CO2. CO2 is carbon dioxide. Okay. It's also already a very neutral pollutant. So you don't need carbon dioxide to make ozone. What you need to make ozone is lots of NOx, lots of VOC, volatile organic compounds, and lots of sunlight. So during the daytime, if you draw ozone graphs, diurnal cycle, you'll have a very big peak during the daytime. And as the sunlight goes down, it also goes down. So during the sunlight, a lot of interaction happens between NOx and VOCs, and ozone is produced. Okay. Which of these following gaseous pollutants can directly contribute to aerosol concentrations? So one of them directly contributes to PM 2.5. Basics. Okay, at least 3 or 4 more answers and we'll move forward. Answer is SO2. Why? What's the trick here? Well, not the trick. What are we looking for? So when we say PM 2.5, it's not always primary aerosols. It's also secondary aerosols. So what is secondary aerosols? Secondary aerosols is reaction of gases eventually saturating and becoming aerosols. SO2 goes through a lot of reactions and becomes sulfate aerosols. NOx goes through a lot of reactions and becomes nitrate aerosols. So when we are doing, if you take a sample, go to the lab and do chemical analysis, you will see a lot of sulfate and a lot of nitrate in that sample, along with black carbon, organic carbon, and all that. Black carbon and organic carbon are primary emissions. They come exactly as they are. Okay. You burn a lot of biomass, you get organic carbon, white smoke. It's PM 2.5. Diesel, if you burn, you get soot, black soot. That is black carbon, BC. It's already aerosols. But sulfate and nitrates, they are not originally aerosols. They're gases. They become secondary aerosols. Okay. What is the unit of air quality index? It's important. We use this a lot. We have to know what is the unit of air quality index. Because we're going to calculate it. I'm going to show you a simple Excel file afterwards for exactly this. Okay. Now we have more people joining, 31 people now. Good. Okay. The answer is none. Air quality index has no units. That's the whole idea. Okay. It's an index. Okay. It's not concentrations. Because there's a big confusion. There's a big confusion. I'm not judging you here. When sometimes I've actually seen more people selecting C than the actual answer. Okay. The idea is, why do we use air quality index? We use air quality index to disseminate the information to people who don't understand the technical knowledge, right? So when we say microgram per meter cube, it's a very technical term. ppm, ppb, it's a very technical term. Not everybody understands. So we have this air quality index. Every country has their own methodologies. It's not a standard methodology. It'll be nice to have a standard methodology for all the countries, but it's there. It's very easy. It is disseminated. It is used to give people, ordinary people, in simple language, in color coded. Green is good, no, yellow is moderate, orange is okay, slightly going bad, red is bad, maroon is really bad, like that. Okay. What is the fundamental equation in building an emissions inventory? We want to build an emission inventory. Okay. Eventually, for every city, we want to build an emission inventory. Okay. What is the fundamental equation? How do you build an emission inventory? What are the two things you need to build an emission inventory? Yeah. Yeah. Now, if you don't know I know most of you are from the monitoring background, probably have not done any emission inventory work, but guess. So this is where we build. So like when we say how much emissions are coming, how do you think that number has been calculated? Okay. At least half people answer, then I will move and then we can have some discussion. Okay. 15. Few more, couple more. Guess. No, guessing is very important. Just guess. No. What do you think? Okay. That is the right answer. Okay. Activity multiplied by emission factors. Activity. What is the activity? Okay. You're driving a car. That's an activity. You're burning waste. That's an activity. You're burning coal. That's an activity. Okay. How much coal are you burning? How much fuel are you burning? Okay. How much waste are you burning? Activity. Multiplied by emission factor. How much pollution comes out if you burn certain amount of fuel? That's it. Very simple. Okay. If you understand this concept, you will build the inventory. Okay. This is the basic concept. You have to only understand the concept. Activity multiplied by emission factor. Then You think about activity. You're talking about transport sector. What is the activity? If you're talking about transport sector, what is the activity? Transport, yeah. Driving, vehicle kilometers traveled. How much do you travel? That's the activity, okay? Very simple. If you know I have 100 cars, they travel 40 kilometers a day, okay? Multiply that, you have kilometers traveled. You get an emission factor from some literature. You have an inventory for your cars, okay? Very simple, okay? So if somebody asks how much fuel is consumed in your city, same thing. It's an inventory, energy inventory. So how many kilometers are they traveling? What kind of efficiency, economy do you get? You have cars which travel 10 kilometers per liter. Okay. So if you're traveling 100 kilometers, how many liters of petrol are you going to use? 10 liters of petrol. Done. 100 divided by 10. Finished. Okay. Concept. Now I want to build an inventory for waste burning emissions, open waste burning emissions. What is the activity? I want to build an inventory for open waste burning in my city. So what is the activity in that equation? Open burning, how much waste is burnt? So if you can find a way to calculate how much waste is burnt, you have an inventory. So how do you get to the activity? How do you get that number? That's where modeling comes in. But all that is, again, as I said, nitty-gritties, details. We have to go into different pockets, different reports, get that information. But everything ties back to that equation. Activity multiplied by emission factor. You understand the concept, you will build it. Okay, this is from your monitoring community. Okay, very important. It's an excellent, important thumb rule. Okay, what is the represented area of an air quality monitor? Okay, you have a monitor, a reference grade monitor or something. You took it, you put it. What is it representing? How much area can it represent? What is the thumb rule? Reference monitor. Take a reference monitor. Actually, it applies to any monitor, but yeah, take a reference monitor. Yeah. But that's why I'm asking a thumb rule. There is a thumb rule in the monitoring community. What a monitor represents. What it represents an area. It doesn't represent a city. It represents a certain area. What is that area? Okay, at least a few more answers and then we'll go. Guess. If you go and put it, will it represent a city or an area? Small area, big area, how much area? Okay. Okay, 21 answers. I'm going to go. That is the right answer. 2-kilometer radius. Okay. So this is a thumb rule. Okay. So generally speaking, a 2-kilometer radius is 10 square kilometers, like a 9 point something square kilometers. So round it off to 10. Okay. So if your city is 400 square kilometers, okay, ideally speaking, how many monitors do you need by a thumb rule? 40. 400 by 10, 40. So you need 40 monitors, ideally speaking. But no, running 40 will be too much. There's a lot of money, maintenance, costs. So you optimize. You will say that, okay, I'll put 4 in residential areas, 4 in industrial areas, 4 on the roads, those kind of, and 4 on the background. So you optimize your locations. But General thumb rule. This is a thumb rule. Okay. Any monitor is representative of area 2 kilometer radius. No, no, that co-location is really important. That co-location, you need to be next to each other. Okay, this is only representation. Okay, this is representation. And then here also there are some loopholes. If you're in main city, too many buildings, too many obstructions, this 2 kilometer radius doesn't apply. I mean, there it becomes less and less and less. So there you may need more stations. Okay, so this is why we call it as a thumb rule. If you don't know exactly how much do you need, this is a thumb rule everybody uses, generally speaking. Okay. So what does source apportionment study aim to determine? So this is the definition I mentioned in the beginning. No, when we say source apportionment, what is source apportionment? No, Google, or that's why we have these primers. I want you to take these primers. If you know, just go through them. They're comic books. Go through them and you have a good idea. Okay. Can you help me? Huh? Yeah. Yeah. One. You take one. Then you can just. Okay. I said this many times. Source apportionment. Source apportionment. Okay. What does it represent? Well, what do you like when we do source apportionment? It tells me what? Okay, 21 answers. I'm going to move. Okay. So, what are all the activities that are contributing to my problem? My problem is air pollution. I want to know what are the activities that are contributing to my problem. That is source apportionment. Okay. Want to basically put a number to my problem. Not just how much, but who is responsible for my problem. Okay. Again, this is actually an important thumb rule. This is also a thumb rule. And people don't immediately practice, but it's a thumb rule. Okay, what action is recommended when idling in traffic for more than 30 seconds? So if you have a lot of congestion happening all the time in a city, okay, you don't want to waste the fuel. Okay, how do we do that? No, just one. Take 1 second and then distribute in 1 second. Yeah, if they already have it, then. Okay, few more answers, at least 5 more, 6 more. Then I'll change. Okay. That's right. Turn off the engine. Okay. So when you start the engine and stop the engine, obviously there is some wastage, but that is actually less than idling for 30 seconds. If you keep the engine running for 30 seconds, it will actually waste more fuel than starting it. So if you already know that you're going to stand somewhere for 30 seconds, yeah.
If you are using diesel-powered engine
and you switch it off and you start again, the suit is greater than if you leave it on you.
Yes and no, but if it's already hot, it's not. Yeah. See, in 30 seconds, the engine doesn't get cold. So this restart is actually much lesser. Okay. So for heavy duty vehicles, that's true. But this is more in city, small vehicles, light duty vehicles, like a car. Okay. So what you said is very true for heavy duty vehicles. If a big truck is there fully loaded, then you probably will waste more. That's true. Yeah. Yeah.
So how is opening the engine contributing to reducing emissions?
Because the engine is idling. So when you're idling, you have lots of unwanted pollution, right? So you have incomplete combustion happening, especially for NOx and VOCs. It's incomplete combustion and it basically just comes out all the time. So you don't want that. The idea is to reduce that. Yeah, that's exactly what he said. So, but here in 30 seconds, the engine doesn't get cold. So if it is really cold, the cold start will have higher emissions for sure. But this is not a cold start. We are not idling, I mean, we're not stopping the engine for a very long time. In 30 seconds, the engine doesn't get cold. So it's still hot. Well, that's why I'm saying thumb rule. Hmm. Excellent. I'm liking the discussion. Okay. Main pollutant of volcanic eruptions. I mean, I don't know if there are volcanoes in this area, but main pollutant of volcanic eruptions. If you've taken any environmental classes, then you would have known. If not, guess. Guessing is important. All of modeling work is guessing only. Yeah. Mm. Okay, 4, 5 more. Okay. No more coming answers. No. Guess. Don't leave the question empty. Okay. Sulfur dioxide is the right answer. Okay. So you get a lot of sulfur dioxide. Okay. And it has a huge co-benefits as well. If more sulfur dioxide is there, when the global warming won't happen so much, it actually contributes to cooling. But that's not a reason to put more sulfur dioxide in the air. Okay. But it happens. It's a natural emissions. Okay. So pollutant that gets attached to blood, hemoglobin, and leads to premature mortality. Okay. So this pollutant loves blood. If you're exposed to very high concentrations of this pollutant, you can die in 15 minutes. This is the reason why we basically say that if you're in a traffic congested area, you are better off like rolling the windows down so that you don't get suffocated with this pollutant. Couple more answers and I'll change. 20, 21, 22. Yes. That's the one. Carbon monoxide. Okay. Very important. It loves blood. It attaches to hemoglobin really fast and cuts down oxygen supply to your lungs. Okay. Lightning produces this pollutant in large quantities. No one? I guess everybody's busy reading the books. Hmm? No, in this area, when you have lots of lightning, lightning produces what? Lightning produces this pollutant a lot. So these are all natural sources. When this pollutant, for this pollutant, it's a very important source. Always misunderstood or underestimated. Okay, we have 20 answers. I'm going to move. Okay. NOx. You get lots of NOx. NO and NO2. You get lots of NO and NO2. Okay. One lightning strike, it can produce as much as what a city can produce in a day. Okay.
Sub-region. Because our sub-region experience a lot of lightning. So can it be a precursor for the high NOx being recorded?
Yeah. So the only advantage is most of the NOx is happening vertically. So in the column you have lots of NOx. At the ground level, we'll have little. Eventually, maybe some reactions will happen and then it will come down. But overall, lightnings produce a lot of NOx, especially in the tropics. Their major source of NOx will be lightning. Okay. In the coastal areas, it will be a significant value. Like for example, for Accra, the west coast here, even in west coast of India during the monsoons, we have lots of NOx coming. It's a natural source. We can't help it. Okay. Okay. People who are doing health impacts, especially for you. Okay. If you want to do health impact analysis, these are the two pollutants we use for calculating health impacts. Okay. Huh? You're going to pass? Hmm? Some more? So the big study that happens every year is called Global Burden of Diseases. Okay, they calculate what is the impact of outdoor air pollution and indoor air pollution on health, and they calculate how many people are dying, premature mortality from heart attacks, lung cancer, and all those things. They use two pollutants. It's a global methodology, very common. Yeah. Okay, 22 answers. Some more coming. So it's PM 2.5 and ozone. Okay. So PM 2.5 and ozone contribute when we need the concentrations of those to calculate the health impacts. The global burden of disease studies, they use that. Okay. The good ozone protecting us from UV radiation resides in Ozone on the ground is bad for us. Okay, that's what we use to calculate health impacts. We don't want ozone where we are on the ground. No. Okay, but we want ozone up there. What is up there? What is that area called? We want good ozone where? We don't want any ozone here. On the ground, no. But up there, yes. Hmm? That's the N2 table. Like them pressing away. Okay, two more people. Couple more, please. 19 only. Okay. Stratosphere. Stratosphere is the answer. Okay. In troposphere, that's where we live. This is under the clouds. We don't want it. Okay. We don't want it under the clouds. We don't want it in troposphere. The tropospheric ozone is what we use to calculate all the health impacts. That's also like we try to understand what is contributing to tropospheric ozone because we don't want it. We want ozone in stratosphere. Okay. Again, a term that will used a lot. You will hear it a lot in almost all the conferences, health impact conferences. Okay. We're doing health impacts. You need a COPD. Chronic obstructive pulmonary disorder is associated with ChatGPT working? Okay, a few more. Get me to 22, 23. Okay. Lungs. Pulmonary, lungs. Cardio. Cardio is heart. Okay. Pulmonary is lungs. This is chronic. Yeah, that's a bit tricky. Sometimes we assume that C is cardio and then we say heart. No. Okay. Again, this is from the monitoring community. We are measuring PM10, PM2.5, ultrafine particulates. So what is ultrafine particulates? What size? So all these new monitors are coming. We want to do ultrafine particulates. What is that? You do any ultrafine testing? Vicky? Yeah, you guys do any ultrafine testing here? Ultrafine particulates, do you guys do anything? No. You? I mean, are you even, I mean, are you looking at UFP? And no, you are. That's better. No problem. Yeah.
Independent. So the instrument that is used to assess the fumes for black carbon, we have the readings for the various particles. Yes. So after this, then we can discuss the particular micron that is fine.
Ultrafine particles, yeah.
No.
Okay. No, looks like more people joined. 3 more people joined, but they're not answering. So the answer is 0.1. It's actually 100 nanometers. It's not. So 1 micrometer is submicron. Okay. So ultrafine is 100 nanometers, 0.1 micrometers. Okay. I mean, it's a new field. It's emerging. A lot of new monitors are coming, probably not here. Even in India, they're not doing it. But from the health community, now they started to measure more of ultrafine particulates. Oh, so it's shifting. Okay. Excellent. Ambient air pollution sources are. Ambient air means outdoor air, basically. So technical term is ambient. We call it ambient, means whatever is around us, outdoors. So outdoor air pollution sources are. This one. That question can only an engineer can answer. Are you an engineer? No, because the answer for engineer is always it depends. For every question, answer it depends. Because they want to select everything. Okay, so we have 20 answers. I'll go ahead and okay. That's right. So answer is everything that burns. So it's very important. So we basically neglect the fact that, no, this is again the concept issue. This is never about sources. It's never about transport or industry or cooking or heating. It's about how much fuel or how much waste or how much of that burnable material is getting burnt. Yeah, I realize that maybe that's the question is coming from. So this is more from burning perspective. Yeah, I will change the question a little bit. Okay, yeah. But among these 4 answers, that's the answer. Okay, everything that burns, it's very important. So even when we say source apportionment, ideally speaking, we want that apportionment to fuels. How much coal is being burnt, how much petrol, diesel, gas, waste. Okay, so that's when then you can target. If your problem is coal, okay, then you can find coal is burning where. It makes it a lot more easier. Okay, and in your city, maybe there's a big power plant and most of the coal is being burnt there, right? Then it's very easy to target one particular source. Okay, so it's always, if you burn something, it is contributing to air pollution, as simple as that. Okay. Which of the following statements is true? Let's see. How much do you understand air quality index? Basics. It goes back to the definition of air quality index. Like, why do we calculate air quality index? It goes back to that. As simple as that. As a scientist, I don't like air quality index. I like absolute concentrations. I want absolute concentration. I want micrograms per meter cube. I want how much exactly is there. But air quality index is developed for a very specific reason. Okay. What is that? So a couple more people, 22, 23. Okay. Public awareness. Okay. It's very important. Air quality index is preferred for public awareness because in the general public, if you want to put a post in the newspaper, you want to make sure that everybody understands. Okay. It's like traffic lights. Everybody understands green, orange, and red. Okay. Green means go, orange means something is happening, red means stop. Finished. Same thing, air quality index has been designed for public awareness. Green is good air, red is bad air, maroon is like severe air, like that. Okay, very simple. Okay? Air quality index provides more information than air quality data. No. Okay, in air quality index, you don't know which pollutant is responsible for that air quality index because air quality index is calculated for 6 different pollutants: PM 2.5, PM 10, SO2, NO2, CO, and ozone. All 6. And they pick a severe one. Okay. The severity basically tells you, okay, this pollutant's air quality index is the worst one today. So today's air quality is this. Okay. Even though the pollution is coming from all 6 pollutants, only one pollutant is used to define air quality index for that day. It's only about health severity, nothing to do with absolute values. Okay. Air quality information is preferred for regulatory purposes. No. Okay. Regulatory purposes means compliance. Compliance means, am I above the standards or not? And air quality index doesn't have a standard. There's no standard. It's just purely to tell people whether it's good air or bad air. That's it. Okay. Air quality index value is same as PM 2.5. No. Okay. So you do have some of these monitors that comes out in the market. They basically tell you, oh, this is air quality index, which means that, and they actually mean PM 2.5. There are monitors like that because they don't know the difference between air quality index and PM 2.5. We should be aware of that. If you see something like that, you should tell them, boss, not happening. Okay, this is not correct. Which of the following statements is true? When we're using all these different things, no? Emissions, pollution, concentrations, air quality index, do they all mean the same thing? Or do they mean different things? Sorry, coffee break is delayed, yeah? You enjoying? Excellent. I'm also happy. When again, the idea is concepts. We want to know the concepts. Okay, 22, 21. I'll move ahead. Yeah, it looks like one more person joined. It was 38 earlier, now it's 39. Okay. Okay. Discussions on emissions is not the same as discussions on pollution. Emissions and pollution are Very, very different, completely opposite. Okay, completely opposite. Emissions is what is coming out at the source. Okay, if a car is going, the tailpipe fumes are coming, that is emissions. Okay, pollution is what you are measuring in your monitors outside. Everything is, all emissions are coming into the air, they are mixing. That's what we are breathing. We don't know where that pollution has come from. It's there, it's mixed up. Okay? When we talk about emissions, I know exactly where that emission came from. I'm talking about transport emissions, means I'm talking about how much emissions, how much pollutant has come out from the tailpipes. Okay? That's emissions. When I say pollution, I'm talking about pollution that I'm breathing in the air already. I don't know where it came from. Okay? Very important. When you are presenting your work, don't mix the phrases. Okay? Emissions is not same as pollution. What you're measuring is pollution. You're not measuring emissions. Okay? The last one, discussion on pollutants is same as air quality index. No. Okay? Pollutants are different. Air quality index is different. Concepts. Okay? Maybe I'll skip. How many understand AOD, air quality, optical aerosol index? Okay, 3 people. Okay, I'll skip this question because this is not the right audience. One person answered, that's correct. But best way to reduce air pollution. Best way to reduce pollution. Remember what we just went through in the previous question. Then you will know the answer. Best way to reduce pollution. Now I'll know who the engineers are. Okay, and all those people who said all the above, they are engineers because it's the wrong answer. Okay, we have to control emissions at the sources. Okay, it's not all the above. Okay? You can't increase the monitoring stations to reduce pollution. It doesn't work that way. Emissions monitoring stations are only there to measure how much. Okay, I'm super glad that it says 100% because in a few events I got that 10% to 20% also, because people just assume that no, we are doing this. It's part of the air quality management. Doing monitoring is part of air quality management, but it is only to tell what to manage, not a management solution. Okay, very important. And you can't put vacuum cleaners in the middle of the road because it's I put this because in India it's become a popular thing. People are putting vacuum cleaners on the roads. No, it doesn't work. Okay, I think the last few, just couple more. Okay, I think I'll skip this also because we really haven't, because I understand that not many people have the concept for source apportionment. Okay, the answer here is that one. Okay. The reason why the emissions pollution modeling is the preferred way is because it gives you a large spatial and temporal spread. Okay, that's the first chapter in the book. Okay, in this book, You read it, it's only 3-4 pages. It'll give you an idea of what are the advantages of actually building a representative emissions inventory and going through the motion of understanding what is happening in across the airshed, okay, and building that, and how that is really helps in doing a full source apportionment, trying to understand how much of the pollution is coming from what source, okay. Okay, I'll skip this as well. Yeah, I think this I'll keep. Which of the following statements is true? Oh, one more person joined, 40 now. And everybody got copies of these? Yeah? I mean, if you didn't get any of the copies, please take, yeah? And this also, yeah? If you... Hmm? There are 4. Yeah, 4, 5, I think. You just go, I think you didn't get the small one. That, yeah. Okay, 25 people. Okay, that is absolutely correct. Okay. So this is where we basically completely underestimate. Everybody thinks about low cost, low cost. Low cost is only in the beginning. Buying only. Buying only is low cost. So after that, maintenance, calibration, validation, that is a lot. So every monitor, whether it's a sensor or a reference grade system, doesn't matter. All of them need maintenance. All of them need validation. So this is one of the reasons why I also tell people that don't use the word low cost. It's not low cost. It's just a sensor. It's just a cheaper sensor. That's it. Okay. The activity of monitoring still involves all the steps. So those are the steps we basically defined in there. This is the last one. So I want to see. In real time, we'll see what's happening. Okay. I think medium seems to be the popular one. But generally, why is it medium? Because only half the people answered, is that one? No, I mean, after 20 people, after 40 people, 20 people answered. But no, that's the last question. You understand the concepts. So these are all the small concepts that you have to know. Going forward, doing more modeling, you need to know this. What are the thumb rules? What are the basic equations like activity multiplied by emission factor? You need to know the fundamentals. Okay. Then we can complicate things. Yeah. Okay. Can I? You still doing the coffee break? No. Okay. Cool. Then I'll continue for some more time. Yeah. And the next stage. Okay. So when we say pollution, okay, so how do you calculate pollution? If we have to calculate pollution. So you're measuring pollution, that's fine. Okay. You want to calculate pollution. How do you do it? What's the units of pollution? I mean, what you're measuring. Units of pollution. PM 2.5 is measured in units. Come on, say it. Bolo, bolo. PM 2.5, what you're measuring in your monitors, what is the unit? Micrograms per meter cube. Okay. So if I want to say micrograms per meter cube in English, because micrograms per meter cube is in science terms. But if you want to say that in English, what is numerator? What is on the top? And what is bottom? Micrograms is means micrograms is grams is a unit for mass. Okay, mass of emissions. Bottom is meter cube. Meter cube is volume of air. Okay, so if we want to calculate pollution, what are the two things we need? Mass and volume. Mass is mass of emissions. So if I have a city, let's say this room is a city, okay, I want to calculate how much pollution is in this room. So I need to know how much are the emissions. Okay, how much are the emissions in this box? Okay, and I know the volume of the box. Mass divided by volume, I have pollution. That is like micrograms per meter cube. That's the mathematical definition if you want to do this. Okay. In a very simple term, if you assume your city is a box, okay, Accra is a box. I mean, technically it's not. It's very dynamic. Things are flying in everywhere. Lots of things are coming and going. Lots of things are happening even in the city. But if you don't have much of information, all you have is a simple information. This is the city size. Okay. And I know how much emissions are happening from an inventory. You know how much coal is being burned, how much petrol is being burned, how much diesel, how much gas, how much waste is being burnt, and you have an emission load. Okay, this is the emission load of my city, and this is the airshed size. Technically speaking, we can calculate what could be the pollution in the city. This is called a box model. Okay, so next step. So you're monitoring, but you also want to know like what could have been the emission load to come to this number. I'm measuring 100 micrograms per meter cube in my city. So I want to back of the envelope, not a like full big model type, but I want to understand what will be the emission load in the city that will contribute to 100 micrograms per meter cube. I want to do that calculation quickly. I don't have many resources, I want to do it. So box model is something that one can use to calculate. Okay. Now, volume of air in the city. We know that it's not static, right? So what is the variable you need to make it a dynamic volume?
Okay, so wind speed.
That's it. Okay. If I know the wind speed and if I know where it's coming from, so it's blowing from east or blowing from west or north or south, if I know the wind direction, if I know the wind speed, I know the size of the city. I can calculate how much wind is flowing through. Okay. In a way, it's not a static wind flow, it's a static volume, dynamic volume. I can calculate that. Okay. Now, is the top of the wind fields, top of the air, static? What is that variable that we always, I'm sure you have seen it in some presentation somewhere. what is the top of the wind fields that you need. Here, if it's a room like this, I know exactly the length, breadth, and the height. Multiply the three numbers, I'll get it, volume. But when I'm outside in the air, there is an invisible blanket. What is it called?
Mixing layer height or boundary layer height.
Mixing layer height, the boundary layer height. Okay, so that's the ceiling for a city, for any city. Is that constant? No, that's also not constant. So every hour, that's changing. Okay, nighttime, it's really low because temperatures on the ground are low. Okay, in the daytime, they're very high. They're as high as 2 kilometers, 3 kilometers, different areas. In Accra, it's close to like 2 to 3 kilometers because it's coastal, tropical, nice and hot. So it's that way. But if you go northern, if you go more north, very low. If you in some places, nighttime will be 50 meters, which means that if you put a lot of emissions and it's only 50 meters, concentrations will be very high because high number on the top, emissions, very low volume in the bottom. No, you have very high concentrations. So imagine now a box model. Now we have, I think you understand the concepts, everything, right? Understand? Yes. Okay. So if we have wind fields, wind speed and direction, if we have mixing layer height, hour by hour, and if we have an understanding of the emission load in the city, can we calculate hour by hour what could be the concentrations? Yes, mass over volume. We can calculate the volume when we know the mass. Mass over volume, we can calculate. So that's a box model. Okay. Now the trick is to find the meteorological data. That's where you have to do some work. Okay. But there are also a lot of websites which will give you that information. We can download that and we do it. So this is a box model. Same thing on the website. Here, chemical transport models. So you can download this box model. Okay, very simple. We put the same thing, same calculations here as a box model. All this sheet is doing is for hour by hour, it takes UV, like horizontal wind, vertical wind, that you can get from the fields, calculate the wind speed and wind direction, and you have PBL, potential boundary layer height. Okay, this is the mixing layer height. If the mixing layer height is very high, your concentrations will be low. The mixing layer is very low, concentrations will be very high. Okay, very simple. If emissions are high, pollution will be. Did somebody say crazy? No. Yeah, if emissions are high, pollution will be high because numerator is high. Okay, if emissions are low, pollution will be low. Okay, so even here there is a scenario. Okay, if somebody asks how much is meteorology affecting my pollution levels, is it always only driven by emissions or is it driven by meteorology? If it is driven by meteorology, how much? So you can say that, okay, I will reduce my emissions by 30%, but meteorology is not helping. Sure. Then you have to do a lot more. Okay. So this is a box model. All it does is literally calculates that mass over volume of air, hour by hour, okay, dynamically. So the volume of air that we are using changes with the wind speed and mixing layer height. And on top of that, there are some corrections that happen in the fields. What kind of corrections? What do you think? Meteorological related only? We have to make some corrections. when do you think, when you've seen even in Dan's presentation, even in some of your present data that you might have seen, sometimes pollution levels are really, really low. Why? Yeah, yeah, that's true. If the wind speeds are very high, pollution will be low. That wind speeds are already there, so it's accounted for, it will get accounted. But is there another phenomenon when pollution levels are really low? Irrespective of what the emission load is, pollution is almost.
Maybe persistence in the environment, how long they are suspended in the environment can also contribute to the concentration.
One more try.
Temperature,
Temperature and
humidity.
go one step further on humidity. So let's not go so technical, even simpler, but humidity related only, but simpler. Rain. Okay, wet scavenging. Sorry, did you say that? No, I saw your hand was up. Yeah. Yeah. So that is getting too much into science of coagulation and sedimentation and expansion and all that. But I'm thinking more simpler, even more simpler. Rain. If rain happens, what happens? All the pollution gets scavenged. It all goes away, right? So even in the box model, you want to make sure that if 1 hour, for some hours, if there is rain, you should account for that. I mean, you shouldn't be calculating pollution because you have emissions. No, it doesn't work that way, right? So we have a correction for rain. Okay, same thing. What Jeff was saying about deposition. There's also dry deposition. This is with rain, it's wet deposition. Without rain, it is dry deposition. So that also happens. So very simple box model where we account for dynamic wind fields. You have a emission load, and because the meteorology has information on rain, we can also calculate for wet scavenging also. All it does is calculates that mass over volume with some corrections. Okay, you can quickly do. So this is set up for Delhi. So we can do something similar for other places as well. So if you know the air shed size, okay, if you know the emission load, and you can even have diurnal cycle for your emissions. In the sense, emissions are not the same every hour, right? You have rush hours, you have emissions will be more. Cooking hours, emissions will be more. So you can even put a diurnal cycle in the emissions. Okay, from the monitoring data, you will get the diurnal cycle. I mean, you have an idea of when the emissions are high and when the emissions are low, even during any day. Yeah, you can use that to build a diurnal profile. Same thing for the seasonal profile. Not every season is the same, but at least here, every season will almost be the same. But if you go into the northern latitudes, there winter time will be a lot more higher emissions because in the cold countries, yes, yeah, in the cold countries, wintertime pollution will be higher because heat generation. So people burn a lot of things to make themselves warm. So wood will be burned, coal will be burned, waste will be burnt, and mostly in the house, but it also comes out, right? So you have more emissions there. But pollution is also higher in winter time because a meteorological phenomena. What is that? In the winter time, pollution is also higher because of a meteorological phenomenon. What is that? Chat GPT? No. So I'm just kidding, sorry. Mixing layer height. So because the temperatures are very low, mixing layer height in the winter time is very low. So volume is low, pollution is high. Okay. So it's a very simple thing. Again, the concept, if you know that, without doing any modeling, you will be able to build profiles for pollution. Just looking at that simple equation, mass over volume. If your volume is low, pollution will be high. Volume is high, pollution will be low. If mixing layer height is low, pollution will be high. Okay, because mixing layer low means volume is low, pollution will be high. If temperatures are low, inversion is low, pollution is high. Okay. If you see a lot of rain, pollution is low. Okay. If you see very high wind fields, very high wind speeds, pollution will be, wind speed is high. Huh? Wind speed is high. Pollution will be low. Because wind speed is high, it takes them away because the volume goes up, right? The amount of air moving is very high. Volume of air moving is high. So pollution will be low. Okay. So if you just looking at the meteorological fields, we can build a profile for a city. Okay. So this is the basic information you need to know. Then you can get into the bigger models, gridded models. I can tell you for every district and all that stuff. But eventually the concepts comes down to very simple equation. What is that simple equation? Mass over volume. Okay, maybe I can here then. So mass over volume. Okay, just like we have a fundamental equation for emissions, activity multiplied by emission factors. Same way for pollution, it is mass over volume. So on that, we have much bigger models. We use Python, Fortran, C, big servers. All our models run on AWS, run on the Amazon servers. But equation is the same, mass over volume. So we do it for grid by grid, grid by grid, grid by grid. So you do it for 1,000 grids, 10,000 grids. Okay. Both on the ground and in the air. But equation is the same, mass over volume. Okay. So this box model, we can quickly calculate how much is the diurnal variation and how much is the monthly variation. And we can use this to, oh, it froze. Okay. So all you need in this inputs is that meteorological data. You need the wind speeds, we need the mixing layer height, and we need the rainfall data. And you can actually run a box model. So we have this box model set up. Okay. If you need meteorological data, we also have a platform where you can download the meteorological data. It's pre-compiled. So this is here for India. For different cities, but we have a similar portal for other cities as well. Okay. In general, if you can send us a location saying, okay, we want meteorological data like this to use in the Excel file for city X, we can provide you that Excel file, cut and paste. You have a box model for your place. Okay. Again, this is a box model, but a lot of things can be done in a box model as well. Even before you go to a much complicated program, which will spend 6 months, 1 year to just get it running, even before you do that, something like this will really help you build a lot of base information that you can use to tell a lot of stories. So this calculation is simply using the box model with some base information on like what is the diurnal cycle, what is the monthly cycle of your emissions, and putting in hour by hour metrology, all run in Excel. And it will give you a nice little plot saying, okay, this is the monthly concentrations I'm calculating. Okay. Now, you are running a big monitoring network for your area. Okay. So you have a monthly profile, right? Put it next to it. See whether you are able to generate the same trend or not. Okay. If you're not able to generate the same trend, which means that maybe the emission load you're using could be different, or the monthly profile or diurnal profile that you have input could be different. So you can play with that, okay, to see what emission load will give me the concentrations that I am measuring. Okay, so even before you do a big emission inventory calculation, you will have an idea of what is the emission load in my airshed that is contributing to the kind of numbers that I'm measuring. Okay, this is the monthly profile that I have. This is the diurnal profile I have. Okay, can I replicate that in a simple box model? So it will really give you a lot of background understanding of your own city. All doing in Excel before you go into complicated models. Yeah. The ultimate goal is obviously to do complicated stuff. But if you start there, trust me, you'll be just stuck in getting compiled on those servers, getting programs and running them for compiling. When I have seen how much you guys were struggling to download there's Python and installing and all stuff. So you will go there. Eventually you will go there, no problem. But start with something that you can use. Okay? Very important. Again, going back to fundamentals. If you want to do emissions inventory, fundamental equation is we have to
mass over volume.
Emissions. Activity multiplied by emission factors. Okay. And if I want to calculate pollution, what is the fundamental equation? Mass over volume. Mass over volume. Fundamental equations. Very important. You have to know the concepts. You can then do big things. Okay. So, homework. Who wants homework? Everyone wants homework? Okay. So at least do 1 or 2 quick scenarios on the scenario player that I showed you in the morning. Okay. Okay. Maybe, like, for example, you can do one for Legos. That'll be nice. I know you have lots of monitoring data. Just put in for 10 districts in Legos saying these are the constant averages. It doesn't have to be accurate. Nobody's testing. Nobody's validating that. So an example. Okay. Somebody from Accra can volunteer. Simple. The very first version saying these are my 10 zones in the city. These are my averages. And no, this is how it looks. Yeah. Very simple exercise. Now you have the Excel file with you. The averages that you are measuring in your city, your own data. Okay. What kind of average you're measuring and how does it No, look in a scenario player. Very simple. Yeah? You think I will see a couple of them tomorrow? Yeah? We're not asking you to do any extra modeling. Already you're doing a lot of monitoring. Let's take that data to the next step. Okay? Let's put it to use. Yes? You don't want to go to school? No homework. Try. Now it'll be really interesting for you to operationalize the data that you already have. Okay? The whole concept here, the whole exercise here, the whole course is around operationalizing information that you already have. Okay? Even in the box model here, two important things that are immediately useful from the monitoring data are these profiles, these diurnal profiles. This is exactly earlier, who was showing before Gift came? James. Yeah, he was showing a lot of those diurnal cycle profiles, monthly profiles. He was building all those things. So that information is useful in modeling because that data is coming from ground reality. So that's the profile that we are using. So we can use the profile in the box model where we are doing all the analysis for the whole city, not just for one point. Now we're doing it for the whole city. Okay. So this is where what you're monitoring comes in. So they are not independent stories. They are interlinked stories. Like what you're measuring, how does come into modeling here, like this. Okay. Same thing for the monthly profiles as well. If there is a monthly profile, we want to know. Okay, where will we know? We will know it in the monitoring data. You get that monthly profile and use it in the file. Yes? Okay, so I'm not asking you to build this. You can play with it, but at least for the version 1, a simple scenario player, okay? If you can do a simple scenario player for your city, that'll be really great to see. Okay? Okay, now I think we have little time. So quick questions. So we have 15 more minutes. General questions.
So, like considering the dry season whereby the Sahara Desert moved through to the Amazon. Now, in that sense, down here, or let's say from the source of transport, the level of pollution or the dust will be reducing whilst it's increasing at the end. So when you ask the question about the effect of wind, whether it's going to increase or decrease, we are discussing it depends on where we are looking at. Yes, so that's what I just want to, it is a comment.
So that's the next step. So even box models, you can account for background concentrations. So that's something that we have not included in this one. This is a version 1. So there's a version 4 where, again, complications. Every version gets more and more. So background concentrations are definitely important, especially places where outside contributions are more. Okay. There, you can actually have a column for background concentrations also. That you can get it from a global model. So we have a method to do that. So we can also put that in Excel and it automatically calculates that. Yeah. But the concept of mass over volume, if the wind is high, pollution is low, from a mathematical perspective, okay? We are not talking about whether a source is coming from Sahara or not. Of course, that'll change the whole story. Yeah. But mathematically, do we understand that or not? If wind speeds are high, pollution will be low. Temperatures are low, pollution will be high. Okay. Yeah. Yeah. Wait.
So please, in your presentation, you mentioned that when rain comes, there's fall off. So in winter, we said that due to the burning activities, we are going to have high concentrations of pollutants. But then what would be the role of the snow? Because similar to rain, I was expecting a fall off as well. So in what situation during winter will you have high concentration of pollutants and then low?
So if the snow is falling, then you'll have scavenging. That's part of precipitation. Okay. But after the snow has fallen, it's on the ground, it has no impact. But the temperatures are still low, means heating is going to continue. Okay. Heating continues means we have more emissions. More emissions means more pollution.
So in the case of temperature inversion, where in the evening sometimes you have suspended pollutants, how would that play also in that environment?
Yeah. So the inversion comes in the volume calculations. Okay. So inversion is low means volume of air for vertical dispersion is very low. So low volume, high concentrations. So we have in the ABCs. So if you look at W, okay, so how weather plays role. So exactly what I'm talking about. If the inversion layer is low, pollution is high, volume is low. So wind speeds are high, pollution will be low. Under W, weather. Yeah, and in this ABC. Okay. So nitty-gritties, I mean, we can get into more of that. Any more questions? But think about it, as I said, playing is very important. You have to play with these tools. So more you play, more questions you will have, then I'll also be able to help you taking it forward. Okay. Eventually, we want to do a full story for the city, not just a box model, not just an Excel file, a full story. We want to do that. But we want to make sure that you understand what goes into doing these stories. Okay. Now, otherwise, what happens is the Kampala presentation I gave in the morning, it will be like that. Now, in 10 minutes, the whole story of Kampala. It doesn't make any sense. Okay, you don't understand what happened. So the idea is we want you to understand, how we can build a story for the city. Okay. So all of Kampala and Adis work is online. I'll share the links on the WhatsApp group, so you can download the big presentation I showed you. That's also online, so you can just download that and take a look.
Yeah, but I don't know where are we going to use maybe particle counter or something to get portion or okay.
But in the big models we use, so those are automatically accounted for. Yeah. So when we do the full scale modeling, so the sea salt, lightning, volcanic eruptions, wind blown dust, the dust from the desert regions, all of them are automatically accounted for in the big models. Okay. But those are all automatically included, means all you have to do is, okay, include this, and it will do it. But you have to know whether to include it or not. Okay. So that's where the concepts come in. If you understand, okay, these are my big things in my area that I want to include, These are the ones I want to calculate and make sure they're accounted for. So the idea is, if you understand that, everything else is just a model. Okay. Maybe in 3-4 years from now, AI will do all the modeling. But what AI is not going to do is interpret it for you. It will only tell you how much is this. No, that's it. How do you interpret? You have to interpret. Okay. Yeah. If you interpret means that you have to know the background, you have to know the concepts. Then you are still in business. Yeah. Okay, packing.
Thank you so much, and apologies for no coffee break. I think we were all enjoying the session, so yeah.
Sorry.
So please, we'll take our dinner. We'll pick our dinner from our normal stand. Tomorrow we have sessions from Sarath. He will continue from today, and then Cosmos would end with us tomorrow. We have Dr. Mike Giordano on it, but then unfortunately he's not available. The time zone, we are about 8 to 9 hours ahead, and so the time is not too favorable for him. So Cosmos will take us for the final session for tomorrow. So in the morning we have Sarath and then Cosmos in the afternoon. Now, I think that's the only announcement. Tomorrow, so we'll start at 8:30. We would want to hear from you. So for the 2 minutes pitch presentations, if you have like at most 3 slides, just 2 minutes, tell us what you are doing or what you intend to do with regards to air pollution, air quality, or emissions, anything that you are doing in regards or relating to what we are working on here. So the first 30 minutes will be dedicated to that. Then Sarath will start at 9, if that's okay. Kindly send us your slides this evening, tonight, or first thing in the morning before 8:30. Yes, so name it with your, sorry. Yes, something like that.
Well, I got copies, everybody, but there seems to be a lot of copies here. So, yes.
No, just share one. You take one, they'll come for it.
My table. 1, 2, 3. My table.
Taking 4.
Everyone has.
No, this one we don't have. Most people didn't get that.
Yeah. All the copies are here.
So yeah, 2, 3 for my table.
So, Nat, please, we are done for the day. Thank you all so much. Okay, we will ask Dr. Kwabena Ofosu to pray for us.
Gracious Lord, we thank thee, O God, for taking us through a successful deliberation today. We pray that you protect us and send us to our various destinations and give us the strength so that we can come and join and continue with such an incredible exposition. In Jesus' name we pray with thanksgiving. Amen.